James Webb just found a galaxy so distant, its light left when the universe was only 290 million years old. And it may already contain oxygen. That's a chemical fingerprint that should take time the cosmos supposedly didn't have. So what are we really seeing? An impossible galaxy, a mistaken distance, or a crack in the timeline that sets the age and expansion of the universe? What Webb delivers is not a photograph of the past, but a measurement, light sorted into wavelengths, where each notch matters. In that pattern, astronomers read distance, temperature, motion, and the fingerprints of elements forged inside stars. But at extreme redshift, those fingerprints arrive stretched and faint, and the difference between certainty and illusion can be a fraction of a pixel. Oxygen is not just stuff in space, it is a timestamp, because it must be manufactured, released, and mixed. If it appears too soon, the problem is not merely one galaxy, it is the pace of the first stellar lives and the calendar we use to date the cosmos. To understand why, we have to walk backward through the chain of inference that turns infrared light into a cosmic age. We will see how Webb's instruments isolate ancient photons and why this telescope took decades to build. We will watch how a redshift becomes a distance, and how a distance becomes a time since the Big Bang. By leaning on a model of expansion that has organized modern cosmology for a generation. That model is powerful because it links many kinds of evidence into one coherent picture. Yet its strength is also its vulnerability. When a measurement lands at the edge of the observable universe, small uncertainties can swell into enormous consequences. A line can be misidentified, a calibration can drift, a foreground object can masquerade as a primordial one, and a statistical fluke can look like a new era. And still, the opposite possibility remains on the table, quietly, uncomfortably, and with growing interest. Perhaps the early universe was more efficient than our simulations allow, forming massive stars that lived fast and enriched their surroundings with startling speed. Perhaps the first galaxies assembled earlier, brighter and stranger than the textbooks predicted. Or perhaps the cosmic clock itself, the one that assigns ages to the most distant light, is not as settled as it appears. So we begin with the evidence, then follow the machinery that produced it, and then confront the blueprint that translates it into history. Along the way, we will meet other early galaxies that seem too bright, too massive, or too organized for their supposed era, and we will ask whether they are mirages, rare peaks, or a genuine population. By the time we return to the original signal, you will know exactly what would need to be true for oxygen to appear so early, and exactly what would need to be wrong for it to disappear. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From Webb's infrared eye to the Lambda CDM timeline that dates the first galaxies, we will trace how one result can stress test an entire cosmological framework. And when the story reaches the Hubble tension and the next generation of surveys, the mystery will narrow, not by drama, but by better evidence. A single spectrum lands on a screen, and the headline follows. Oxygen detected in a galaxy at the edge of the universe. One word shifts the entire story, because oxygen is not just chemistry. In astronomy, oxygen counts as a metal, meaning anything heavier than helium. That definition sounds strange on Earth, yet it is practical in space, where hydrogen and helium dominate almost everything we see. Metals are forged inside stars, then scattered by winds and supernovae. In the cores of massive stars, helium fuses into carbon, and carbon can fuse into oxygen. Those reactions require extreme temperatures and pressures, the kind only gravity can sustain for millions of years. When the star dies, its interior is no longer locked away, and the galaxy inherits the debris. So oxygen is a timestamp, stamped by stellar lives and violent deaths. The claim sounds simple, but it carries a threat. This galaxy's light has traveled about 13.4 billion years to reach us. We see it as it was when the universe was roughly 290 million years old. That number is not a footnote. It is the cosmic clock reading. It places the object in an era when structure should be young, fragile, and chemically primitive. Yet the spectrum suggests maturity, and maturity requires time. To understand why this is unsettling, we need a timeline that feels real. The Big Bang sets the starting gun, then the universe expands and cools. In the first minutes, the simplest nuclei form, leaving mostly hydrogen and helium, with only traces of lithium. Much later, the plasma clears, and the cosmic microwave background is released, an afterglow that still fills the sky. For a while, there are no stars, only dark hydrogen and helium drifting through expanding space. That interval is sometimes called the cosmic dark ages, and it is not poetic exaggeration. Without stars, there is no visible light, only cooling gas and the slow pull of gravity. Tiny density ripples, seeded in the early universe, begin to grow into the first dark matter halos. Gas falls into those halos, compressing and heating, then cooling again as it tries to settle. The first stars ignite later, and they are thought to be massive and short-lived. Their radiation begins the long process called reionization, when neutral hydrogen becomes ionized again. Ultraviolet photons from early stars and galaxies tear electrons from hydrogen atoms, changing how the intergalactic medium absorbs and transmits light. Reionization is not a switch that flips everywhere at once. It is patchy, with bubbles of ionized gas expanding around the earliest luminous sources. Early galaxies assemble in that glare, building mass while the intergalactic medium changes state. In standard narratives, heavy elements accumulate gradually, generation by generation. The first stellar generation begins with pristine gas, then ends by polluting its surroundings. Later stars form from that enriched material, and their spectra begin to show stronger metal lines. Dust grains can also form from metals, altering how starlight is absorbed and re-emitted. Over time, a galaxy's chemistry becomes a record of how many stellar lives it has already spent. Now place 290 million years on that arc. It is early, even by early universe standards. It is before reionization is complete and near the dawn of the first galaxies. It is the moment when any galaxy we can see should be close to its beginning. If oxygen is already present in notable amounts, then star formation started earlier, proceeded faster, or enriched gas more efficiently than expected. Or we are being fooled by the data, by our assumptions, or by the model itself. The observational claim is anchored to a number. Redshift Z is reported around 14.32, which is extreme even for James Webb. Redshift is the stretching of light as space expands, so wavelengths arrive longer than when they were emitted. The higher the redshift, the more the wavelength has been pulled toward the infrared, where human eyes cannot see. In practice, that means a galaxy that once glowed in ultraviolet can show up as a faint infrared smudge. Redshift is also a distance measure because expansion accumulates over the photon's journey. It is also a time measure because looking far away means looking back in time. The same equation that maps redshift to distance also maps it to cosmic age, once an expansion history is assumed. Faraway objects are time machines, and their photons arrive as evidence. On screen, that evidence looks like a jagged line, with bumps that may be real or may be noise. At z about 14, the universe is not just distant, it is young. A galaxy there is seen before most galaxies have had time to grow large. It is seen before many models expect stable disks, complex dust, or rich metal lines. Yet the spectrum appears to show an oxygen feature, and oxygen implies prior stellar processing. That is why the word oxygen changes everything. It suggests that the galaxy is not a pristine first-light object. It suggests it has already lived through at least one cycle of starbirth and death. Even one generation is enough to matter, because massive stars evolve quickly. A star tens of times the sun's mass can burn through its fuel in only a few million years. When it explodes, it can seed its surroundings with oxygen and other elements almost immediately, by cosmic standards. Here is the tension that makes the mystery. People hear oxygen and translate it into a rough intuition. Heavy elements take about 1 billion years to build up. That intuition is not a law of nature, but it captures a set of assumptions. It assumes star formation ramps up slowly in small halos, because early structures are shallow and easily disrupted. It assumes enrichment is limited by how fast gas turns into stars. It assumes supernovae eject metals, but much of that material escapes shallow gravitational wells. It assumes early feedback blows gas out and delays the next generation, turning growth into a stutter rather than a surge. It also assumes we are not preferentially catching rare extreme objects in small survey volumes. Under those assumptions, strong oxygen lines at 290 million years feel too early. But the universe does not promise to follow our intuitions. A few massive stars can create oxygen quickly because massive stars live fast and die young. A burst of star formation could enrich gas in tens of millions of years, especially if the gas is dense and rapidly recycled. A dense region could trap ejecta efficiently instead of losing it to intergalactic space. A galaxy could appear chemically mature if we are seeing a compact starburst, not a settled system. The problem is not that oxygen is impossible. The problem is whether the reported oxygen is real, and whether its implied abundance fits within plausible early histories. Spectral lines can be subtle, and subtlety is dangerous at the edge of detection. A line can be shifted, broadened, or blended with neighbors depending on gas temperature, density, and motion. Even the presence of ionized oxygen implies a strong radiation field, which itself tells a story about the stars. That is where the investigation begins. The protagonist is a galaxy, but the setting is the edge of the observable universe. The distance is not scenery. It is a filter that turns photons into clues. Those photons have crossed a changing cosmos, passing through hydrogen that can absorb specific wavelengths. Along the way, the intergalactic medium can carve away parts of the spectrum, leaving gaps that mimic intrinsic features. Every measurement is made through expansion, through intervening gas, and through an instrument with its own biases. At these redshifts, a small error in wavelength becomes a large error in age. A misidentified line can move a galaxy across hundreds of millions of years, and that shift rewrites the entire timeline. The cosmic clock is precise only if the inputs are correct. James Webb Space Telescope is the key player because it can see what Hubble could not. Webb is tuned for infrared light, where the earliest galaxies are shifted. Its mirror collects far more light than Hubble's, and its detectors are cooled to reduce their own thermal glow. In visuals, the telescope is a gold hexagon in darkness, an engineered eye kept cold so it can notice warmth from the ancient universe. Its sensitivity makes faint objects measurable, and its spectrographs turn smudges into physical claims. A spectrum is not a picture, it is a ledger of wavelengths. Peaks and dips correspond to atoms, ions, and conditions in gas. When a team says oxygen, they mean a specific feature at a specific observed wavelength.
They mean a line that should appear only if the galaxy's gas contains oxygen in an excited state. Yet every step from photon to headline can introduce uncertainty. The redshift can be photometric, inferred from colors, or spectroscopic, pinned by lines. Photometric redshifts can be fooled by dust, by unusual stellar populations, or by line contamination. A sharp break in brightness can mean hydrogen absorption at high redshift, or it can mean something closer with different physics. At the edge of the universe, those possibilities can look uncomfortably similar. Spectroscopic redshifts can be fooled by noise, by overlapping features, or by miscalibration. The instrument must subtract backgrounds, correct detector artifacts, and align wavelengths with extreme precision. At the edge of detectability, a few data points can dominate interpretation. The claim is bold because the signal is faint, and faint signals demand careful skepticism. In a plot, the difference between discovery and mirage can be a bump only a few pixels wide. The other key player is LAMCDM, the standard model of cosmology. It combines cold dark matter with a cosmological constant, and it predicts how structure grows. It sets the expansion history that converts redshift into age, and it anchors that history with measurements like the cosmic microwave background. It gives a framework for when halos collapse and when galaxies should appear. It also sets expectations for how quickly gas can cool and form stars in the first deep potential wells. If a galaxy at Z 14.32 is already enriched, lambda CDM is not automatically broken, but it may be strained, or it may require rare conditions, or it may expose missing physics in early star formation. Simulations have to approximate processes that occur far below their resolution, like turbulence, radiation transport, and the way supernovae couple energy into gas. When a spectrum disagrees with the simulation, the question becomes precise. Which assumption is failing, and by how much? So the stakes are clear, and they cut in three directions. First, the measurement could be wrong, meaning the redshift is lower or the line is not oxygen. Second, the interpretation could be wrong, meaning oxygen is present, but not in the abundance implied, or the feature arises from another process. Third, the model could be incomplete, meaning early galaxies formed and enriched faster than our simulations capture. Each answer changes a different part of the story. One challenges the data, one challenges the inference, and one challenges our cosmology. And each possibility carries its own kind of discomfort, because each forces us to admit a different weakness. Are we misreading a fragile signal? Are we overconfident in a physical translation? Or are we missing a chapter in how the first galaxies behave? The mystery is not only what the line is, but what our reaction to it reveals. We will treat those three answers as the map for this documentary. We will follow the photons back through the pipeline, from spectrum to redshift to physical properties. We will ask what oxygen detection actually means in practice and what alternative identifications exist. We will test what kinds of early star formation histories can produce oxygen quickly without violating what we already know about the early universe. We will compare those histories to the constraints of lambda CDM and the cosmic microwave background.
We will keep the cosmic clock in view because the age estimate depends on the expansion history we assume. And we will keep returning to the same visual motif, a thin feature in a spectrum, highlighted by a cursor, carrying a weight far larger than its size. For now, the mystery remains suspended on a thin line in a spectrum. If that line is oxygen at Z14.32, then a galaxy is speaking from an era we barely understand. It is telling us that metals appeared early, and that structure grew up fast. If the line is not oxygen, then the episode becomes a lesson in how easily the edge of the universe can mislead us. Either way, the signal forces a confrontation with our methods and our models. To judge the claim, we must first understand the instrument that found it and why it took 30 years to build. To judge the claim, we have to understand the eye that saw it and the physics that shaped what it could possibly see. Webb is not just bigger than Hubble. Webb is tuned for a different universe, one where the first light arrives stretched, diluted, and faint. Cosmic expansion does not only push galaxies away as if space were an empty stage, it also stretches the space between wave crests as photons travel, dragging their wavelengths to longer values and lowering their energy on arrival. In practical terms, ultraviolet and visible starlight can slide into infrared by the time it reaches us. A galaxy that once blazed in hot, young UV can arrive as a dim infrared whisper, and that whisper is easy to miss. At redshift 14, the shift is so extreme that ordinary optical telescopes are nearly blind because their detectors are simply looking in the wrong part of the spectrum. Redshift is more than a distance label. It is also a clock, because the light has been traveling since the universe was young, when galaxies were still assembling their first generations of stars. The higher the redshift, the earlier the snapshot, and the more severe the stretching of the spectrum. That stretching also spreads a galaxy's light over a wider range of wavelengths, reducing the flux in any single band. The first light is not only far away, it is redistributed into a regime where the sky and the telescope itself can compete with it. This is why infrared matters for first light, and why seeing farther is not a simple matter of magnification. The earliest galaxies are expected to be dominated by massive blue stars and ionized gas, because short-lived stars form quickly and burn fiercely. Their strongest signatures begin in the ultraviolet and optical, where hydrogen and metals imprint sharp edges and bright lines. By the time those signatures cross more than 13 billion light-years, they land in the near-infrared and sometimes the mid-infrared. If you cannot measure infrared precisely, you cannot read the early universe's ledger, its ages, its star formation, and its chemical hints. Webb's wavelength range is built around that fact, and it is engineered as a deliberate bridge between regimes. It covers roughly 0.6 to 28 microns across its instruments, spanning the edge of visible red into near-infrared and out to mid-infrared. That span is not a luxury. It is the difference between seeing a high redshift galaxy's spectral break and missing it entirely, because the break can slide across filters as redshift climbs. In deep field work, the ability to sample many adjacent bands is how you avoid fooling yourself. Sensitivity is the other half of the equation, and it is where the romance of first light meets harsh counting statistics. The first galaxies are not only redshifted, they are intrinsically small, distant, and often low in dust, which can make their light bluer in the rest frame but still faint in total power. Every photon matters because the signal is weak and the background is relentless. And background in infrared is not just the sky, it is also the observatory, the optics, and the detector's own noise. Webb's primary mirror is the blunt instrument of sensitivity, and its scale is easiest to appreciate when it fills the frame. It is 6.5 meters across, made of 18 hexagonal segments that act as one surface, like a honeycomb of gold-lit panels. A larger mirror collects more light, and more light means deeper exposures and fainter detections at the same signal-to-noise. In deep fields, collecting area becomes time saved or depth gained, and time is the currency of discovery. The mirror is coated in gold because gold reflects infrared efficiently across Webb's working range. That choice is not aesthetic. It is a throughput decision that pushes more ancient photons onto detectors rather than losing them as heat. When the target is a galaxy near the edge of the observable universe, small efficiencies compound into discovery, because each optical surface is another chance to waste the signal. Segmented mirrors are not simple mirrors, and Webb's is less a single object than a controlled system. Each segment has actuators that adjust position and curvature, aligning the whole surface to nanometer precision, which is smaller than the wavelength of near-infrared light. Webb had to become diffraction limited at near-infrared wavelengths, meaning its sharpness must be limited by physics, not by misalignment or thermal drift. Without that stability, faint galaxies blur into the background, and spectra lose contrast as light smears across pixels. Even the idea of focus becomes a choreography at this scale. After launch, the segments had to be identified, moved, and phased until their separate images collapsed into one coherent point spread function. In visuals, it is like watching 18 ghostly stars merge into a single sharp one, as if the telescope is learning to see. That learning is not metaphorical. It is wavefront control, and it is the difference between a deep field full of smudges and one full of measurable galaxies. The mirror alone is not enough, because infrared astronomy has an enemy that optical telescopes can mostly ignore. Anything warm glows in infrared, including the telescope itself, and that glow is not a minor nuisance. A warm observatory can drown its own targets in thermal emission, turning the instrument into a bright foreground that overwhelms the faint cosmic signal. In infrared, the telescope is always at risk of becoming the brightest thing in its own images. That is why Webb is a cold telescope, and why its silhouette is dominated by a shield that looks more like a sail than a scientific instrument. Its 5-layer sunshield blocks sunlight and Earthlight, and it enables passive cooling of the optics by allowing heat to radiate away into space. The shield is made from capton, thin and reflective, with layers separated so heat leaks outward step by step rather than flooding the cold side. Each layer reduces the heat flow, and the temperature drop is the difference between signal and self-noise. Passive cooling is a design philosophy and a constraint, and it shapes everything from pointing to scheduling. It avoids heavy cryogenic tanks that would limit mission life, because stored coolant eventually runs out. It also demands a stable orientation, because the shield must always face the sun, keeping the telescope's cold side in permanent shade. Webb's entire observing strategy is shaped by the need to stay cold, and that need quietly dictates where it can look at any given time. The sunshield is also a risk multiplier, because it is not a rigid plate, but a deployable structure with little tolerance for error. It had to unfold perfectly after launch, with hundreds of release mechanisms and tensioning steps, each one a potential single point of failure. One snag could have ended the mission before the first image, leaving only engineering data and a cautionary tale. Webb's promise was always paired with fragility, an audacious design balanced on a sequence of irreversible moves. Cooling is not uniform across the observatory, and that unevenness is part of the instrument's story. The near-infrared instruments operate cold enough with passive cooling because their detectors and optics can tolerate higher temperatures without being swamped by thermal photons. The mid-infrared instrument needs even lower temperatures, so it uses an active cryocooler to reach the required range. Mid-infrared sensitivity is purchased with complexity, because the colder you go, the harder it is to keep the system quiet and stable. Webb's orbit is the other pillar of its design, and it is chosen for geometry as much as for distance. It does not circle Earth like Hubble. It travels to the second Lagrange point, about 1.5 million kilometers away, where the gravity of Earth and Sun helps it maintain a stable position relative to both. In wide shots, it is a small machine hovering in a vast gravitational landscape, holding station where forces nearly balance. L2 is not a magical parking spot. It is a region where Webb can keep Sun, Earth, and Moon on the same side, behind the sun shield, so the cold side remains cold. That geometry minimizes stray light and keeps temperature steady, which matters because thermal changes can subtly distort optics and shift detector behavior. Thermal stability is observational stability, especially for long exposures where you stack hours of data and expect the instrument to behave the same way throughout. L2 also enables continuous viewing of large parts of the sky, and that continuity is a quiet superpower. Webb can stare for hours or days without Earth eclipses interrupting observations because it is not repeatedly passing into shadow. Deep fields depend on uninterrupted integration because stacking many exposures is how faint galaxies emerge from noise. At the edge of detection, continuity becomes a scientific advantage, and interruptions become visible as lost depth. But L2 comes with a cost that is both practical and psychological. It is too far for astronauts servicing with current capabilities, and the mission was never designed around routine repairs. There is no rescue shuttle waiting in the wings. Webb was built for one launch, one deployment, and then whatever the hardware can endure, which makes every design choice feel final. That risk shaped the program's history, and it helps explain why the telescope feels like a long-delayed promise. Webb took roughly 30 years from concept to launch, pushed by technical ambition and political turbulence, with milestones that often arrived later than planned. The mirror, the shield, the detectors, and the deployment sequence all carried first-of-their-kind hazards, and each hazard demanded testing, redesign, and more testing. The mission was not late because it was careless. It was late because it was trying to do something no previous observatory had attempted. Budget politics became part of the engineering story because large science missions live inside shifting priorities. Costs grew as requirements hardened and failures were prevented rather than fixed in space. And prevention is expensive because it must be proven. Schedules slipped because the mission could not tolerate unknowns, and unknowns hide in mundane places like wiring harnesses and hinge tolerances. The price of seeing first light was learning to fear every overlooked bolt and cable, every small thing that could stop a big telescope from unfolding. Testing became a mission inside the mission, with its own drama and its own stakes. Components were chilled, shaken, and cycled to simulate launch and space because materials behave differently when they are cold and weightless. Optical alignment was rehearsed because it could not be improvised after deployment, and because the system had to work the first time. The goal was not elegance. The goal was survival long enough to do science, and survival in space is never guaranteed. Science is ultimately done by instruments, not by mirrors, and Webb's instruments are designed to turn faint smudges into physical statements. Webb carries a suite built to measure distance, composition, and conditions, because astronomy is inference from light. Each instrument answers a different part of the same question, and together they reduce ambiguity. What is this object? How far is it? And what is it made of? NIRCam is Webb's primary near-infrared imager, and it is the workhorse for the iconic deep-field views. It takes deep images through multiple filters, building a galaxy's colors across wavelength, and those colors encode the shape of the spectrum. Those colors are not just pretty. They are the raw material for photometric redshifts, where a distance is inferred from how the spectrum is shaped, even when individual lines are too faint to isolate. Photometric redshifts rely on a key feature that acts like a cliff in the spectrum. Neutral hydrogen absorbs light shortward of the Lyman limit and strongly suppresses flux blueward of Lyman alpha, so the spectrum drops sharply at a predictable rest wavelength. As redshift increases, that sharp drop moves into redder filters, sliding step by step across NIRCam's band passes. A galaxy can appear to vanish in one band and reappear in the next, creating a dropout signature that points to a specific redshift range. In visuals, the dropout method is almost cinematic. One filter shows empty darkness where a galaxy should be, and the next filter reveals a faint reddish speck in the same position. That on-off behavior is the clue, but it is also the trap, because nature can imitate the pattern. The method is powerful because it is fast, and it is dangerous because it is indirect. Dropouts are powerful but ambiguous, especially when the signal is near the noise. Dusty galaxies at lower redshift can mimic a high redshift color break because dust reddens spectra and can suppress blue light in a way that looks similar. Strong emission lines can also contaminate broadband filters, making a galaxy look more distant than it is by boosting flux in one band. Photometry is a first pass, not a verdict, and the best candidates are the ones that survive multiple consistency checks. NIRSpec is Webb's near-infrared spectrograph, built for confirmation and for physical diagnosis. It spreads light into a spectrum, letting astronomers identify emission and absorption features at specific wavelengths, rather than guessing from broad colors. Those features can lock down a redshift and reveal gas conditions, including ionization and density indicators. Spectroscopy turns a candidate into a physical object, with measurable lines that can be compared to models. NIRSpec's multi-object capability matters in practice because deep fields are crowded with faint sources. It can observe many targets at once using microshutters, tiny controllable apertures that open for selected galaxies and close to block unwanted light. It can also use fixed slits and an integral field unit for different science goals, from precise single-object work to spatially resolved spectroscopy. The flexibility is designed for surveys and for detailed follow-up, because discovery and confirmation have different needs. MIRI extends Webb into the mid-infrared, where the universe looks different again. It can image and take spectra where dust emission and longer wavelength lines become accessible, and where cooler components of galaxies can contribute more strongly. For the earliest galaxies, MIRI can probe rest frame optical features that have shifted beyond the near-infrared, offering another way to test a redshift. It is slower and more background limited, but it reaches a different set of diagnostics, and sometimes that difference is decisive. FGS and NIRIS support both pointing and science, and their role is easy to underestimate until you picture a long exposure. The fine guidance sensor stabilizes the telescope so exposures stay sharp, holding the line on guide stars with extreme precision. NIRIS can do slitless spectroscopy and specialized modes, capturing spectra without a slit for many objects in a field. Stability and calibration are part of the measurement, not an afterthought, because a drifting image can turn a faint line into a false one. With these tools, Webb does something specific, And the specificity is what makes the claims testable. It translates redshifted ancient light into measurable chemistry, and it does it by separating wavelengths cleanly enough to recognize patterns. The chemistry is inferred from spectral fingerprints, where atoms and ions emit or absorb at known rest wavelengths. When those fingerprints shift together by the same factor, distance and composition become linked in a single observation. This is where the oxygen claim lives, and it is worth being precise about what oxygen means in this context. Astronomers do not mean oxygen gas in the everyday sense, and they do not mean breathable air drifting between stars. They mean ionized oxygen producing characteristic forbidden lines, often discussed as O3 at 500.7 nanometers in the rest frame, a transition that is strong in many star-forming regions. At extreme redshift, that line is shifted into the infrared, where Webb operates, turning a familiar optical diagnostic into an infrared target. At Z around 14, even familiar lines land at unfamiliar observed wavelengths, and the numbers become startling. A rest frame optical line can move into the near-infrared or mid-infrared depending on the exact redshift, and that determines which instrument can see it. That makes line identification both possible and perilous, because a spectrum may contain only a few detectable features. When there are only a few features, each one carries heavy interpretive weight, and each one must be interrogated. Line identification has caveats at the frontier, and those caveats are not academic. Noise spikes can masquerade as lines when the signal is faint, especially if you search many wavelengths and then highlight the strongest peaks. Lines can blend if resolution is limited or if the galaxy has broad velocity structure from outflows and turbulence. Calibration errors can nudge wavelengths enough to change which line seems to fit, and small shifts matter when you are matching patterns across a sparse spectrum. Even when a line is real, the physical inference is layered because line strength is not a single variable thermometer. O3 strength depends on oxygen abundance, but also on ionization state, gas density, and the hardness of the radiation field, meaning the typical energies of the photons produced by stars. A young, intense starburst can boost certain lines without requiring extreme metallicity, because hot stars flood the gas with ionizing photons. Oxygen detection is a clue, not a full chemical inventory, and it must be placed in context with other lines and continuum shape. There is also a deeper implication hiding behind the word oxygen, and it is why the claim feels so dramatic. Oxygen is not made in the Big Bang in meaningful quantities, so it must be forged in stars and dispersed by stellar winds and supernovae. If oxygen is present very early, then stars must have formed, lived, and died quickly enough to enrich the gas, and that timeline becomes part of the mystery. The question is not only whether a line exists, the question is what kind of stellar population could create it so soon. Confirming a redshift is therefore a procedural battle, and the procedure is designed to reduce self-deception. First comes the photometric estimate from near-cam colors and the dropout pattern, which narrows the possibilities but does not settle them. Then comes spectroscopy, ideally detecting multiple lines that agree on the same redshift, because agreement is harder to fake than a single feature. The more lines, the less room for coincidence, and the more robust the interpretation becomes. At Z near 1432, confirmation is extraordinary and hard to secure, partly because the universe becomes an adversary. The Lyman alpha line is often absorbed by neutral hydrogen in the early intergalactic medium, removing an easy redshift anchor that works well at later times. That forces reliance on weaker lines or on continuum breaks, which are harder to measure when the signal is faint. The universe itself hides the simplest evidence,
because reionization is incomplete and neutral gas is still common. Teams must also separate the galaxy from foregrounds, and this is where the image on screen can be misleadingly clean. A faint high redshift source can sit near brighter objects whose light leaks into the extraction, and the leakage can distort colors and spectra. Background subtraction becomes delicate because the sky and telescope contribute their own infrared glow, and because detectors have subtle systematics that must be modeled. At the limit, analysis choices can shift significance, which is why independent reductions and cross-checks matter. This is why Webb's engineering choices are not separate from the science claim, but are woven into it. The mirror sets the photon budget, determining how quickly the signal rises above noise. The cold design suppresses self-emission, so those photons are not buried under thermal background. The L2 orbit stabilizes temperatures and pointing, so long integrations remain coherent, and coherence is what makes stacking exposures meaningful. Every layer of Webb's design aims at one outcome, and the outcome is not a picture, but a measurement. Capture redshifted first light, disperse it into a spectrum, and read the fingerprints that imply distance and chemistry. The oxygen question begins as an engineering question about whether the signal is trustworthy, and then becomes an astrophysical question about what the signal implies. In that sense, Webb is both a camera and a lie detector, though the interrogation still depends on the questions we ask. The 30-year build is part of the suspense because it created a telescope that can reach the edge and also a dataset that is easy to overinterpret. Webb can see astonishingly far, but it cannot make the universe simpler, and it cannot supply missing context by itself. It delivers spectra that demand models, assumptions, and careful humility, because the early universe is a regime where our intuitions were trained on later times. When the data are sparse and the stakes are high, caution becomes part of the scientific method. Now the story turns from hardware to interpretation, because photons alone do not come labeled with dates. Webb gives us wavelengths and fluxes, and it gives them with unprecedented clarity in the infrared. To turn those into ages, masses, and timelines, we translate through a cosmological model, connecting redshift to expansion history. The model is lambda CDM, and it is the ruler we use to convert redshift into history. Now the story turns from hardware to interpretation. Webb gives wavelengths and fluxes, and it delivers them with exquisite stability. But those numbers are not yet history. They are calibrated counts shaped by detectors, optics, and background subtraction, still waiting for a cosmological translation. To turn light into a timeline, cosmology supplies the conversion, an agreed-upon ruler for distance, age, and growth. That conversion is lambda CDM, the standard model of cosmology. It is not a single idea, and it is not a single equation, but a compact accounting of what the universe contains and how it evolves. In practice, it is a framework that ties geometry, expansion, and gravity into one coherent narrative. It also specifies how small early irregularities grow into the structured sky we actually observe. Lambda CDM says ordinary matter is about 5% of the cosmic budget. It says dark matter is about 27%. And it says dark energy, written as lambda, is about 68%. On screen, those fractions can look like a clean pie chart, yet each slice carries a different physical role. The chart is simple, but the physics underneath is layered, and that contrast is part of its power. Those numbers are not philosophical preferences. They are fitted parameters, cross-checked across many datasets.
and they set the expansion history that turns redshift into time. They are constrained by patterns in the sky, not by aesthetics, so changing them is never a casual choice. When the parameters shift, even slightly, the inferred ages at extreme redshift can move by tens of millions of years. Ordinary matter is the part that forms stars, gas clouds, and oxygen lines. It interacts with light through electromagnetism, cools by radiation, and clumps into the visible structures telescopes actually image. It is also the only component that can make chemistry, because chemistry requires charged particles and photons. In the early universe, it begins as a thin gas, then becomes a complicated mixture of plasma, molecules, dust, and metals. Dark matter is the scaffolding that ordinary matter falls into. It does not emit or absorb light, but its gravity dominates the growth of structure from the earliest times. In visual terms, it is the invisible architecture, an underlying mass map that the glowing galaxies merely trace. We infer it through its pull, in rotation curves, in cluster dynamics, and in the subtle shear patterns of gravitational lensing. Dark energy is the smooth component that accelerates expansion at late times. In the simplest version, it behaves like a constant energy density of empty space, so as the universe expands, the total amount of that energy effectively grows. That counterintuitive behavior is why it eventually overwhelms matter's gravitational pull. It does not clump into halos, so its signature is written into the global stretching of space itself. Lambda CDM became the organizing framework because it links early universe simplicity to late universe complexity. It explains why the cosmic microwave background is smooth, yet galaxies and clusters exist at all. It also explains why the universe is close to geometrically flat within the measurement errors. The model's elegance is that one set of parameters must satisfy all of these facts at once. Historically, this blueprint did not arrive all at once. The CDM part gained traction as galaxy rotation curves and cluster dynamics demanded unseen mass, and as simulations showed that cold dark matter naturally builds the cosmic web. The lambda part returned later, after supernova surveys revealed that expansion is speeding up, not slowing down. In the late 1990s, that result landed like a reversal, because gravity was expected to break the expansion, not let it run away. The cosmic microwave background is the opening snapshot in this model. It is the afterglow released when the universe cooled enough for electrons and protons to form neutral atoms. In a visualization, the fog clears, and radiation that was once trapped suddenly streams outward in every direction. The moment is called recombination, although the more practical point is transparency. Photons finally travel freely. At that moment, light decoupled from matter and began free streaming. The CMB preserves a map of tiny density fluctuations at the level of tens of microkelvin. Those temperature variations correspond to slight differences in density and velocity, minute ripples that later become enormous structures. They are also a record of pressure waves in the early plasma, frozen into a pattern we can still measure. The CMB is also a measurement of scales. The pattern includes a characteristic angular size set by sound waves in the early plasma, and that acoustic scale anchors many cosmological parameters. It is one reason lambda CDM can convert a redshift into a cosmic age with such confidence. The peaks in the CMB power spectrum act like a ruler, one that has been checked and rechecked across experiments. Those fluctuations are the seeds of everything that follows. In lambda CDM, gravity amplifies them over billions of years, turning slight overdensities into halos and filaments. The process is slow at first, then increasingly dramatic, as small advantages in density compound over time. A region that is only slightly denser than average can, given enough time, become the birthplace of a galaxy cluster. The model's power comes from how much is fixed by that snapshot. Given the CMB pattern and a few parameters, the later distribution of matter becomes highly constrained. In other words, the early universe is like an initial condition file. Change it, and the entire later movie changes. That is why the CMB is so central, because it limits how creative we can be about the later story. Cold dark matter is the key assumption about the invisible component. Cold means the particles move slowly compared to the speed of light when structures begin to grow. That coldness is not about temperature in a household sense, but about momentum and free streaming length. The slower the particles, the less they erase small-scale density features by streaming out of them. Slow particles do not smear out small fluctuations. They allow small clumps to survive, collapse early, and then merge into larger structures as time passes. If dark matter were hot, fast particles would wash out small-scale structure, and the first galaxies would form later and differently. Even warm dark matter would subtly soften the smallest halos, changing the predicted abundance of early star-forming sites. This is the hierarchical picture. Small halos form first, then merge into bigger halos, and galaxies assemble through accretion, mergers, and repeated episodes of star formation. A simulation makes it vivid. Threads of matter thicken, knots brighten, and the web becomes a network of nodes and bridges. The camera can fly through a lattice of filaments, dark matter first, then gas following, then stars igniting where the density peaks. Hierarchical growth is not just a cartoon. It is a quantitative expectation that shows up in simulations, in halo mass functions, and in how clustering evolves with redshift. It also appears in statistics like the correlation function, which measures how strongly galaxies cluster at different scales. In lambda CDM, those statistics are not decorative, they are tests, and they punish models that grow structure too fast or too slow. Baryons, the ordinary matter, ride on that dark matter backbone. Gas falls into halos, heats by shocks, cools by radiation, and sometimes forms stars if conditions allow. The gas must also shed angular momentum, because rotation can support it against collapse even when gravity is strong. In early halos, a little extra heat or turbulence can decide whether gas settles into a disk or never settles at all. In the early universe, those conditions are hard to satisfy. Small halos have shallow gravity, and early star formation can be disrupted by radiation and supernova feedback. A single generation of massive stars can heat and expel gas, temporarily shutting down the very process that created them. The first galaxies are therefore expected to be intermittent, lighting up, fading, then lighting up again. Cooling is the bottleneck, and cooling depends on microphysics. Primordial gas lacks metals, so it relies on hydrogen and helium lines, and on molecular hydrogen, which is fragile under ultraviolet light. If molecules are destroyed, the gas stays warmer, and warmer gas resists fragmentation into many small stars. In plain terms, hot gas is puffy, and puffy gas does not break into dense, star-forming clumps easily. That is why lambda CDM tends to predict a slow buildup of mature galaxies. The first objects are expected to be small, bursty, and chemically primitive. Their light should flicker in episodes, rather than glow steadily like later, well-fed galaxies. Even their shapes are expected to be messy, because early mergers and feedback can keep them dynamically unsettled. The timeline implied by lambda CDM begins with recombination and the CMB, then a long period with no stars. Neutral hydrogen dominates, and the only light is the fading afterglow. Visually, it is a universe filled with dark gas, where structure grows in silence. The sky would be full of matter, yet almost empty of visible sources, an ocean without lighthouses. This interval is called the cosmic dark ages. Structure grows invisibly in dark matter, while baryonic gas cools only gradually and struggles to fragment efficiently. Gravity is working, but the universe has not yet built the luminous signposts we use to track it. In animation, halos appear as faint gravitational wells, deepening while the surrounding gas hesitates at their edges. Then, the first stars ignite, often labeled Population 3. They are expected to form from pristine hydrogen and helium, with no metals to help cooling. In artistic renderings, they appear as isolated beacons, rare, intense, and short-lived. Their radiation is harsh because metal-free stellar atmospheres tend to produce very hot, blue spectra. With inefficient cooling, the first stars are often modeled as massive. Massive stars burn hot, live briefly, and end as supernovae or direct collapse, depending on mass. Their lifetimes can be only a few million years, which is cosmologically instantaneous. In that short span, they can flood their surroundings with ionizing photons and begin altering the chemistry of the next generation. Those first stars trigger the next phase. Their ultraviolet radiation begins reionization, the process that reionizes neutral hydrogen in the intergalactic medium. Reionization matters because it changes the transparency of the universe and alters how gas accretes into small halos. Once the background becomes more ionized, small halos can struggle to hold on to gas because heated gas has more pressure support. Reionization is not instantaneous. It proceeds in patches, with ionized bubbles growing around early galaxies and quasars, then overlapping as sources multiply. A useful visual is a dark fog punctured by expanding spheres of light, separated first, then merging into a connected network. The boundary between neutral and ionized regions is not a clean wall. It is a ragged frontier shaped by density, radiation, and time. As ionized regions expand, the remaining neutral hydrogen becomes harder to find, yet it leaves distinctive fingerprints. It can absorb background light, carving troughs and breaks into spectra, and it can damp certain emission features. Even without seeing the gas directly, we can infer its state from what it blocks. The spectrum becomes a silhouette of the intergalactic medium, drawn by absorption rather than emission. The first galaxies emerge within that transition. They form in the earliest halos that are massive enough to hold gas against heating and feedback. Their growth is a contest between gravity pulling inward and radiation and explosions pushing outward. In close-up visuals, you can show gas streams feeding a compact core, while outflows vent along paths of least resistance. In this sequence, 290 million years after the Big Bang is extremely early. It sits near the onset of widespread star formation and well before reionization is complete. In human terms, it is like arriving minutes after the first sparks, then finding a city already half-built. The metaphor is deliberately unsettling because it captures how compressed the available time really is. That is why a mature-looking galaxy at Z around 14 feels provocative. It seems to appear not at the beginning of the story, but after several chapters have already happened. The immediate question is not whether it can exist, but what had to happen quickly for it to look that way. Did it form in an unusually massive halo? Or are we misreading the clues that make it seem evolved? To see why oxygen matters, we need the basics of chemical evolution. Big Bang nucleosynthesis produces mostly hydrogen and helium, with only trace lithium.
The early universe is therefore chemically simple, and that simplicity is one of Lambda-CDM's cleanest starting conditions. It also means that any heavier element we detect at high redshift must have been manufactured locally, inside stars, after the first collapse. Oxygen is not made in meaningful amounts in the Big Bang. Oxygen is forged later, inside stars, through helium burning and subsequent fusion stages in massive stellar cores. In the final phases, layered shells of fusion build heavier nuclei, and oxygen becomes one of the dominant products. This is stellar alchemy with a deadline, because the stars that make oxygen fastest are also the ones that die fastest. When massive stars die, they eject newly made elements. Supernovae and stellar winds push oxygen into surrounding gas, where it can later be ionized and emit lines. In a visualization, shock fronts race outward, sweeping up material and enriching it like dye mixing into water. Yet the mixing is uneven at first. Bright knots of enriched gas can coexist with large volumes that remain almost pristine. Enrichment, therefore, requires time and repetition. Gas must turn into stars. Stars must evolve. Explosions must distribute metals, and the metals must mix into star-forming regions. Each step has its own time scale, and the slowest step often sets the pace. The clock is not only stellar lifetimes, it is also the time it takes for enriched material to cool, settle, and participate in the next round of star formation. Mixing is not automatic. Metals can remain in hot outflows, escape shallow halos, or stay in pockets that do not immediately form the next generation of stars. Turbulence, inflows, and repeated feedback events can stir the gas, but early galaxies are small and easily disturbed. A young halo can lose enriched gas in one burst, then spend tens of millions of years reaccreting fresh, mostly metal-poor material. The oxygen line, often discussed in early galaxies, is O3, a forbidden transition of doubly ionized oxygen. Forbidden does not mean impossible. It means the transition is unlikely and occurs in low-density gas where collisions are rare. That detail matters because line strength depends on the physical state of the gas, not only on how much oxygen exists. In nebular conditions, O3 can become a spotlight, bright when the ionizing radiation is intense and the electron temperature is high. So when people say oxygen implies at least 1 billion years, they are compressing several assumptions into one number. The number is not a clock. It is a model-dependent inference. It is a shorthand that can be useful, but it can also hide the uncertainty inside the word typical. At very early times, typical may be the wrong concept, because the first systems can be extreme by construction. It assumes a typical initial mass function, often similar to later epochs. It assumes many stars are low mass and long-lived, so enrichment builds gradually across multiple generations. If instead early star formation favors massive stars, the enrichment curve steepens dramatically. In that case, oxygen can appear quickly, while the long-lived stars that dominate later galaxies have barely begun to form. It assumes star formation efficiency is modest in small halos. It assumes feedback expels gas and delays the next burst, lowering the net rate of chemical buildup. In early, shallow potential wells, a single energetic event can remove the very fuel needed for continued enrichment. The same feedback that makes oxygen can also scatter it, throwing metals into the intergalactic medium instead of keeping them in the next star-forming cloud. It assumes metals mix on timescales comparable to dynamical times. It assumes the oxygen we observe traces the bulk gas,
not a small region dominated by a recent event.
If we are seeing a compact, intensely irradiated pocket, the spectrum may exaggerate how mature the whole system is. A single bright H2 region can dominate the light, even if the surrounding galaxy is still chemically young. It also assumes we are not seeing an extreme outlier. In a small survey volume, the first rare peaks can dominate what we detect, even if they are not typical.
The earliest massive halos are statistical flukes, rare but not forbidden, and they can bias our first impressions. The first objects we find are not necessarily the first objects that exist. They are the first objects bright enough to announce themselves. Lambda CDM has room to maneuver inside those assumptions. It can accommodate bursts of star formation that convert gas rapidly, especially in unusually massive early halos.
In that picture, a galaxy's apparent maturity is not a slow accumulation, but the aftermath of a short, intense episode. The light we see could be the flare of a brief starburst caught at exactly the moment when nebular lines are strongest. It can accommodate a top-heavy initial mass function in primordial conditions. If most early stars are massive, then oxygen production is fast and the delay time shrinks.
The same choice also increases ultraviolet output, which can strengthen ionization-driven lines like O3. It also changes the feedback environment because massive stars inject more energy per unit mass, making early galaxies both brighter and more fragile. It can accommodate rapid enrichment from very massive stars that live only a few million years. A single intense burst can seed oxygen quickly, at least locally.
The question then becomes whether the oxygen spreads into the regions that dominate the observed emission. In the earliest systems, enough oxygen to see a line may not mean oxygen everywhere, and that distinction matters. It can also accommodate that strong O3 emission does not require high metallicity. Line strength depends on ionization, density, and radiation hardness, not only abundance. A hard radiation field can push oxygen into higher ionization states, and high electron temperatures can make certain lines bright, even at low oxygen content. In other words, the line can be loud because the gas is excited, not because the galaxy is old. But Lambda CDM is not infinitely flexible. The expansion history is tightly constrained by the CMB and related measurements, and that history sets the age corresponding to Z equals 14.32. If you change the clock, you must also change the CMB-derived ruler that the clock is built from. The ruler is not just one measurement, it is a network of interlocking constraints. The matter content is also constrained. The amount of dark matter in baryons affects how fast structures grow, and those parameters are not free to drift arbitrarily. Too much early structure would imply a different growth rate, which would leave imprints in lensing and in the CMB itself. The universe is not allowed to grow new galaxies in secret because gravity leaves receipts. The CMB-derived parameters lock in a baseline prediction for early halo abundance. If too many massive halos appear too early, the model must reconcile that with the CMB map. In that sense, the CMB is not just a picture of the past, it is a contract that later structure must honor. The contract is statistical, not deterministic, but it is still strict enough to make surprises meaningful.
This is where the notion of tension enters. In cosmology, tension means different datasets prefer parameter values that cannot all be true within one model. It is a technical word, but it carries a narrative charge because it signals that our cross-checks are doing their job. The point is not drama for its own sake. The point is that precision creates the possibility of disagreement.
Tension is not a headline about failure. It is a diagnostic that the web of cross-checks is pulling in different directions, forcing us to inspect assumptions and systematics. Sometimes the resolution is mundane, and sometimes it reveals a deeper gap in our modeling. The history of cosmology is full of such moments, where an apparent crack either closes or widens into a new idea. The field has lived through tensions before, and it is living through one now. The Hubble tension is the best-known example where early and late universe measurements disagree on the expansion rate. It is a reminder that even a successful blueprint can have stress points. When the stress persists, it raises a quiet question. Are we missing a subtle systematic or a subtle piece of physics? The oxygen at Z14 claim is not the same kind of tension, but it rhymes with it. It pits an early-time observation against a timeline anchored by early-time physics. It also tests whether our recipes for early star formation are realistic or merely convenient. If the recipes are wrong, the fix might be astrophysical rather than cosmological, but the data will not tell us that automatically. If the galaxy is truly at Z equals 14.32, then its age is set by the lambda CDM ruler. If its spectrum implies significant oxygen, then its internal history must be extremely compressed. The universe would have had to build stars, make metals, and reorganize gas with astonishing speed. And it would have had to do so while the surrounding intergalactic medium was still in the middle of changing phase. That compression can be achieved in some scenarios, but not in all. The question becomes whether the required star formation and enrichment are plausible, or whether the blueprint is missing ingredients. And behind that is a more unsettling question. How often do we mistake brightness for maturity? A young system in a violent starburst can look older than it is, simply because it is temporarily overexposed. One missing ingredient could be astrophysical, not cosmological. Simulations approximate star formation, feedback, and radiation transport, and early conditions may amplify those uncertainties. When resolution is limited, subgrid models decide how gas turns into stars, and those choices can shift predictions by large factors. Even the escape fraction of ultraviolet photons, how easily radiation leaks out, can change the ionization state that sets line strengths. Another missing ingredient could be observational. A single line can be misidentified, a redshift can be biased, and a noise feature can masquerade as a detection. At extreme distances, even small calibration errors can move a feature enough to change the story. The spectrum is faint, the background is complex, and the stakes are high, so every reduction choice matters. A third possibility is that the cosmological conversion from redshift to age is slightly off. That would imply changes to expansion history, which would ripple into many other constraints. Any such change must still preserve the CMB's acoustic pattern, the large-scale distribution of galaxies, and the success of gravitational lensing tests. The blueprint can bend, but it cannot break its own foundation without consequences. The reason this feels troubling is that lambda CDM's success is built on coherence. It is powerful because it makes many predictions at once, and those predictions usually agree. When coherence holds, a spectrum becomes more than data. It becomes a timestamp. The universe starts to feel readable, as though light itself carries a reliable date stamp across billions of years. A mature early galaxy threatens that coherence because it targets the model's most distinctive expectation. Structure should assemble hierarchically, and maturity should be rare at the beginning. If maturity is common, then either the growth is faster than expected, or our indicators of maturity are misleading. The deeper issue is not one galaxy, but what it would imply about the whole early population. So the tension is not only about oxygen, it is about the pace of growth, the efficiency of early star formation, and the reliability of the cosmic clock we use. It is also about interpretation, whether we are reading the spectrum as a biography, when it might be a snapshot of a single dramatic moment. In the early universe, a brief moment can dominate what we see, because everything is compact and intensely luminous when it ignites. Now return to the specific galaxy and its reported redshift. The number Z equals 14.32 is not just distance, it is a claim about the universe's age at emission. It is also a claim about how much the universe has expanded since that light began its journey. Redshift is a stretching of wavelength, but it is also a stretching of context, because it ties a single spectrum to the entire expansion history. In a visual sequence, the galaxy sits at the edge of a deep field, a faint smudge among many. Then the spectrum appears as a ribbon of light, stretched and thinned, with peaks and valleys that must be interpreted. The drama is that the interpretation is not optional. It is the only way to turn photons into a place on the timeline. A tiny bump in that ribbon can become a headline, but only if the chain of inference holds. From here, the chain must be reconstructed step by step. Photons become a spectrum. The spectrum becomes a redshift. The redshift becomes an age, and the lines become chemistry. Each step sounds straightforward, yet each step depends on modeling choices that can subtly steer the conclusion. The chain is strong when many features agree, and it is fragile when one feature carries the weight of the whole claim. Each link has assumptions that can fail quietly. The next chapter follows that chain and asks where the claim is strongest and where it can still slip. The goal is not to dismiss the result, but to locate exactly where uncertainty lives. In science, that location matters because it tells us what to measure next and what to doubt first. We began with an oxygen feature that seems too early. Now we have the blueprint that makes it feel too early, and the constraints that make the feeling testable. The blueprint is not a fragile theory, but it is a precise one, and precision is what makes anomalies meaningful. If the anomaly survives, it does not merely add a detail, it forces a recalibration of expectations. At the edge of the universe, faraway light becomes a forensic record. If Webb's earliest galaxies truly carry oxygen so soon, then either stars lived fast or the blueprint needs revision. And if the blueprint needs revision, we must ask which part bends first: the astrophysics, the observations, or the cosmic clock itself. Now return to the specific claim and rebuild it from the rawest measurement. A faint infrared source is flagged in deep imaging, then promoted into a candidate with a number attached. That number is Z equals 14.32, and it is both a distance proxy and a time claim. On screen, it begins as a few pixels that rise just above the background, barely there, yet persistent across exposures. The field around it is crowded with other specks, and the eye must be trained to ignore the brighter distractions. The first step is deliberately unromantic, because astronomy starts with counting photons. The detector records electrons freed by incoming light, and the pipeline turns those counts into calibrated flux. Behind the scenes, bias frames, dark current maps, and flat fields are applied so that the final image reflects sky, not electronics. At these limits, the difference between real and noise can be a handful of photons spread over hours. The image looks smooth from afar, but zoom in and it becomes grainy, like mist lit by moonlight.
Even the background has structure, with subtle gradients that can tilt a measurement if they are not modeled. A single pixel is never the point, because the telescope's point spread function distributes light into a small pattern. The candidate is therefore measured with apertures and PSF fitting, and each choice changes the inferred flux by a small amount. Those small amounts matter because the signal-to-noise ratio hovers near the threshold where false positives begin to breed. When a source is this faint, the uncertainty is not just statistical. Systematic effects start to dominate. The question becomes uncomfortably basic. Are we measuring the galaxy or measuring our own reduction choices? Redshift is wavelength stretching caused by cosmic expansion, not a Doppler shift through static space. Space itself grows, and light traveling through it is stretched along the way. This is why the same galaxy can be described without implying it is racing through a fixed void. The scale factor is 1 divided by 1 plus z, so at z 14.32, the universe was about 1/15th its current size. In plain terms, every cosmic ruler was shorter, and every region was denser. Matter was also more tightly packed into filaments, so the first halos formed in an environment that was physically harsher and more pressurized. Every spectral feature is shifted by the same factor, so a rest wavelength becomes about 15.32 times longer at the detector. A line emitted in the ultraviolet can arrive as near infrared, and an optical line can drift into wavelengths our eyes never see. That simple multiplication is the heart of the claim, and it is also the trap. If the factor is wrong, then every downstream inference, age, mass, chemistry, tilts with it. The drama of z equals 14.32 is therefore not the number itself, but the cascade of consequences it triggers. That stretching is why Webb matters, because the early universe speaks in infrared by the time it reaches us. The telescope is not merely bigger than its predecessors, it is tuned for this translation. Its gold-coated mirror gathers faint light, while its cold instruments suppress their own thermal glow. Visually, the observatory's sunshield is like an artificial night, keeping the detectors in deep shade so they can listen. In animation, the mirror segments lock into a single surface, and the faintest galaxies become a test of that alignment. Ultraviolet starlight and optical nebular lines slide into near-infrared bands, where background and calibration become decisive. The background is not empty, because zodiacal light and instrument noise add a soft haze. The detectors also carry signatures of their own history, persistence, hot pixels, and subtle striping that must be corrected. Calibration is not a footnote, because tiny errors in flat fields or dark current can mimic faint structure. The signal is faint, and the inference chain must be checked link by link. The mystery lives in that chain, each step plausible, yet each step vulnerable. Redshift becomes a look-back time only after we choose a cosmological model. The universe does not hand us a clock, we build one from parameters. Under lambda CDM parameters consistent with the CMB, Z around 14.3 corresponds to roughly 290 million years after the Big Bang. That number is startling because it compresses everything we know about galaxy building into a brief cosmic dawn. It is also conditional because the mapping from Z to time depends on the expansion history. In other words, the same observed spectrum can imply slightly different ages depending on which cosmic ruler we adopt. Change H0 or matter density and the age shifts, which is why the conversion is never model-free. Even within lambda CDM, small parameter changes move the answer by millions of years. Millions of years may sound generous, but at this epoch, it can decide whether one or two stellar generations fit.
In the background, the Friedmann equations quietly translate redshift into time, turning a spectrum into a chronology. The equations are simple to write down, yet they encode a universe whose early pace was set by radiation, matter, and then the slow rise of dark energy. The discovery pipeline begins with deep multiband imaging, usually from NIRCam. Webb stares for hours, sometimes days, collecting exposures that are later stacked. Each exposure is dithered, so the target falls on different pixels, and detector quirks average out. The deep field is a tapestry of tiny smudges, arcs, and points, each one a different distance. The human eye sees beauty, but the algorithm sees measurements, fluxes, uncertainties, and correlations. What looks like a serene patch of sky is, in practice, a matrix of probabilities. Astronomers search for a dropout pattern, where flux vanishes blueward of the Lyman break. This break is not a property of the telescope. It is a physical cutoff created by hydrogen absorption. Neutral hydrogen in the galaxy and the intergalactic medium absorbs short wavelength light, creating a sharp step in the observed colors. The physics is atomic and unforgiving, because hydrogen's cross-section rises steeply at the Lyman limit. In effect, the universe itself draws a boundary in the spectrum, and we use that boundary as a ruler. That ruler is powerful, but it becomes blunt when the data are sparse. A high redshift candidate appears in redder filters and disappears in bluer ones. The images are often shown as colored composites, where the candidate glows red while the blue channels are empty. That emptiness is the clue, but it is also an invitation to over-interpret. At the detection limit, disappears can mean truly absent or merely buried beneath noise. A single upward fluctuation in a red filter paired with a downward fluctuation in a blue one can sketch a break that is not really there. Photometric redshift codes fit templates to the measured colors and return a probability distribution. The templates encode expected galaxy spectra, including breaks and emission lines, then compare them to the observed fluxes. At the frontier, that distribution can be broad, multi-peaked, and sensitive to small photometric systematics. A tiny shift in one filter's flux can move the preferred redshift by whole units. The output is not a single answer, but a landscape of possibilities. The most honest plots show that landscape, with the exciting peak sitting beside quieter alternatives. The next step is to ask, what could fake the dropout? This is where the romance of first light meets the discipline of skepticism. Brown dwarfs in the Milky Way can mimic red colors with molecular absorption bands. Their atmospheres contain water and methane features that carve out parts of the spectrum, producing a false step. In a deep field, a nearby faint star can masquerade as a distant galaxy, an imposter hiding in plain sight. Historically, this kind of confusion has haunted surveys, from early photographic plates to modern infrared catalogs. Dusty galaxies at lower redshift can suppress blue light and imitate a break, especially when signal-to-noise is low. Dust grains absorb and scatter short wavelengths, reddening the spectrum and dimming the blue filters. A galaxy at Z2 or 3, heavily obscured, can look surprisingly similar to a pristine galaxy at Z14. The ambiguity is not a failure of effort, it is a consequence of limited information. When only a few broadband points define the spectrum, different physical stories can land on the same colors. Strong emission lines can also distort broadband colors. A lower redshift galaxy with intense line emission can brighten one filter and skew the photometric fit upward. In broadband imaging, a narrow line can dominate the flux in a wide filter,
making the continuum appear higher than it is. This effect is especially treacherous when the line falls near the center of a filter, where throughput is highest. The pipeline therefore tests alternative solutions, not just the most exciting one. The goal is not to prove a miracle, but to eliminate the mundane.
Teams also check morphology and motion, because stars and galaxies behave differently. A point source profile and measurable proper motion argue for a nearby dwarf star. Proper motion is subtle, yet over years it can reveal a local object. A resolved or slightly extended profile supports a galaxy, though lensing and PSF effects complicate that judgment. Webb's point spread function has structure, and faint sources can blur into shapes that mislead. Even the act of stacking exposures can slightly broaden a source, so morphology is suggestive rather than decisive. Gravitational lensing is both a help and a hazard. A foreground cluster can magnify a background galaxy and make it detectable. The visual signature can be dramatic, thin arcs and stretched smudges curving around invisible mass. Yet magnification depends on a mass model, and errors in the model propagate into inferred luminosity, size, and stellar mass. Lensing can whisper "ancient," while quietly exaggerating what we think we see. The same cluster that reveals a faint object can also distort its apparent brightness into a misleading extreme. Before spectroscopy, contamination risk remains the central worry. The candidate list is filtered by consistency across instruments and reductions. Astronomers compare independent reductions because pipelines make choices about background estimation, cosmic ray removal, and pixel weighting. Independent teams often reprocess the same exposures because small choices in background subtraction can change faint fluxes. When the signal is near the noise floor, method becomes meaning. A robust candidate is one that survives multiple reasonable methods, not one that shines only in a single reduction. Spectroscopy is the gold standard because it can lock multiple features to one redshift. Imaging gives colors, but spectroscopy gives a map of intensity versus wavelength. NIRSpec disperses the light and searches for emission lines and continuum breaks at specific wavelengths. The spectrum is often shown as a jagged trace with error bars, and every bump becomes a potential headline. A robust redshift is not one line, but a pattern that fits only one solution. In the best cases, the continuum break and the line positions agree, and the uncertainties shrink into a single coherent answer. Historically, this is how redshift became reliable in the first place. Early galaxy redshifts were secured by matching multiple familiar lines, not by trusting a single feature. The same logic applies here, even if the features are faint and the wavelengths unfamiliar. The method is old, but the frontier is new. What changes is the difficulty, because the early universe offers fewer bright features and more absorbing hydrogen between us and the source. At Z above 10, the usual anchor line, Lyman alpha, is often suppressed by the neutral intergalactic medium. During the era of reionization, hydrogen between galaxies can absorb Lyman alpha photons before they reach us. That forces reliance on weaker lines, or rest optical lines, shifted into infrared. The absence of Lyman alpha is not disproof, but it removes a convenient cross-check. It turns the spectrum into a puzzle with fewer pieces. It also hints at the environment, because a strongly neutral medium is itself part of the cosmic story. For Z1432, the Lyman break should land near 2 microns in the observed frame. That sets where the continuum should drop and which filters should see the source. In a clean case, the flux rises in redder bands and collapses in bluer ones, matching the predicted edge. A mismatch between the break position and the photometry is an early warning sign. It suggests either an error in the measurement
or a different physical explanation.
The break is therefore both a distance indicator and a diagnostic of whether the entire interpretation is self-consistent.
Then comes the oxygen claim, which is where the story turns from distance to chemistry. Astronomers infer oxygen through emission lines from ionized gas, not by detecting oxygen atoms directly. The galaxy's starlight energizes surrounding gas, and that gas radiates at specific wavelengths as electrons change energy states. The headline line is often O3, a forbidden transition of doubly ionized oxygen produced in H2 regions. Forbidden does not mean impossible. It means the transition is unlikely in dense labs, yet common in thin cosmic gas. In visuals, the nebula is imagined as a glowing shell around hot stars, with oxygen lines flickering like coded signals. In practice, O3 is interpreted through line ratios and physical models. Its strength depends on oxygen abundance, but also on ionization parameter, electron temperature, and gas density. A hard radiation field from young massive stars can make O3 bright even at modest metallicity. In other words, brightness is not a direct meter of oxygen. It is a combined readout of conditions. The models try to untangle those conditions, but the data at Z14 are sparse. Even the electron temperature matters, because hotter gas boosts collisionally excited lines and can mimic higher abundance. At extreme redshift, line identification is a serious risk because the spectrum may contain only one or two significant peaks. A single peak can match different rest frame lines at different redshifts. The correct answer depends on whether other expected lines are present or absent. This is why the spectrum is not read like a label, but like a code, one that must be cross-checked. The code includes not just wavelengths, but relative strengths, continuum slope, and whether the implied physics makes sense. Line confusion is not hypothetical at these wavelengths. O3 at one redshift can be mistaken for H-alpha, O2, or other features at another redshift. Each alternative implies a different distance, a different age, and a different story. Even small wavelength calibration offsets can flip the preferred identification when the data are sparse. The stakes are high because the spectrum is narrow and the universe is wide. In a plot, the difference can look like a tiny horizontal shift, yet it rewrites hundreds of millions of years. Teams therefore look for consistency across multiple lines and the continuum shape. If O3 is real, H-beta may be nearby in the observed frame, and the ratio can be physically constrained. The O3 to H-beta ratio is sensitive to temperature and ionization, so it cannot be arbitrary. If the ratio is unphysical, the identification becomes suspect. The spectrum must tell a coherent physical story, not just a numerical one. Even non-detections matter, because a missing companion line can be as informative as a detected one. They also test whether the line could be an artifact. Noise spikes become more likely when many resolution elements are searched and only the highest peak is highlighted. This is a statistical trap. If you search long enough, something will look significant. Extraction choices, slit losses, and background residuals can create false features that look line-like. A faint bump can be born from imperfect subtraction of the sky, then promoted by expectation. The discipline is to ask how often such bumps appear in empty regions processed the same way. Assuming the redshift and the line hold, oxygen becomes a clock with a short fuse. Oxygen is forged in massive stars and dispersed by winds and supernovae. It is not primordial in meaningful amounts because the Big Bang produced mostly hydrogen and helium with traces of lithium. So oxygen is evidence of stellar processing, matter that has already lived inside stars. The claim is not merely a galaxy exists, but a galaxy has already evolved. It implies that the first stellar furnaces ignited, burned, and exploded, all before the universe reached 300 million years. The chemical maturity problem is a timing problem, not a philosophical one. In 290 million years, the galaxy must assemble a halo, cool gas, form stars, and survive feedback. It must then recycle enriched gas into new star formation that produces observable nebular emission. Each verb hides complex physics. Cooling requires radiating energy, collapse requires overcoming pressure, and feedback can reverse the entire process. The timeline is short, and the steps are not guaranteed. A viewer should feel the compression, as if the early universe is sprinting, while our models insist it should still be learning to walk. Massive stars can die in 3 to 10 million years, so enrichment can begin quickly. A single burst can seed the surrounding gas with oxygen through core collapse supernovae. The harder part is retention and mixing, because early halos are shallow and outflows are strong. Metals can be blown out, and reaccretion can dilute the enrichment with fresh, pristine gas. The galaxy must not only make oxygen, but keep enough of it where it can be seen. That where matters, because nebular lines come from dense ionized regions, not from diffuse gas drifting into intergalactic space. So the key question becomes cycles. How many star formation and enrichment cycles can fit before we take this snapshot? One cycle can happen fast, but multiple cycles require gas to cool again and collapse again under repeated disruption. Each cycle is a negotiation between gravity pulling inward and feedback pushing outward. The more violent the first stars, the more difficult the second generation becomes. The observation forces a practical question. Did this system find a way to keep rebuilding itself? Or are we catching a rare moment when everything aligned? There are astrophysical accelerators that could compress the timeline. Population 3 stars may be very massive, producing abundant oxygen quickly and injecting intense ionizing radiation. Their lifetimes are short, and their deaths can be energetic, enriching and reshaping their surroundings. A top-heavy initial mass function would steepen enrichment and brighten nebular lines. If early star formation favored giants, the chemical clock would tick faster than in today's galaxies. Yet that same violence can evacuate gas, so the accelerator comes with a built-in brake. Rapid starburst episodes can also front-load the history. If gas collapses efficiently into a dense central region, star formation rates can spike. The visuals here are almost cinematic, an embryonic galaxy flaring as clusters ignite, then dimming as winds clear the gas. Short bursts can dominate the light, making a young system look chemically advanced because the brightest regions are enriched. The observed galaxy may be caught at its most deceptive moment. What we call maturity could be a spotlight effect, where a small, enriched region outshines a larger, more primitive body. Efficient mixing can shorten the delay between enrichment and the next observable H2 regions. Turbulence from feedback can stir metals through the interstellar medium, though it can also expel them. Mixing is not instantaneous, because metals must travel from supernova remnants into colder star-forming gas. Dense environments and continuous inflow can keep fuel available despite losses. The galaxy may be simultaneously losing gas and gaining it, a chaotic balance in a growing halo. In simulation visuals, streams of cold gas thread into the halo like rivers, while hot bubbles push outward in the opposite direction. Early massive halos are another accelerator because deeper gravity wells retain gas and metals more effectively. Rare high sigma peaks in the initial density field can collapse earlier than typical regions. In the language of cosmology, These are statistical outliers, regions where the primordial fluctuations were unusually high.
If the galaxy sits in such a peak, it can be an outlier without breaking lambda CDM.
The question becomes not, can it exist, but how often should it exist? If the answer is almost never, then finding even one becomes a clue about selection and bias. Still, simulations set expectations for how rare such systems should be. The halo mass function at z greater than 10 falls steeply at high mass. A small increase in mass can correspond to a large decrease in abundance, because the early universe has had little time to build large structures. If many massive bright galaxies appear, the implied number density can strain standard star formation efficiency assumptions. The tension is statistical as much as it is physical. It lives in survey volumes, completeness corrections, and the uncomfortable possibility that we are sampling only the brightest tail.
Simulations also include feedback that should suppress early growth.
Ionizing radiation heats gas and reduces accretion in small halos. Supernovae inject energy and momentum that can shut down star formation, especially when escape velocities are low. These processes are not optional. They are observed in nearby galaxies and expected from basic physics. Yet the early universe may couple them differently because metallicities are low and cooling channels change. With fewer metals, gas cools less efficiently in some regimes, but dense regions can still radiate through hydrogen and helium lines, creating a complicated, environment-dependent outcome. The first Webb deep field surprised theorists because some candidates looked too massive, too bright, or too numerous. The surprise is visible in plots, points sitting above model curves, or number counts exceeding expectations.
That surprise does not automatically falsify lambda CDM, but it pressures the subgrid recipes. It forces a recheck of how simulations treat cooling, fragmentation, and feedback at very low metallicity. When models disagree with data, the first suspect is often the messy physics we approximate. The second suspect is always the measurement, because extraordinary claims can grow from ordinary biases. At this point, the mystery splits into three competing explanations. The galaxy formed unbelievably fast, with early physics more efficient than we modeled.
We are misreading the signal through redshift error or line misidentification. Or the observation is biased toward extreme objects that are not representative. Each explanation preserves something and sacrifices something. Either our astrophysics, our measurement, or our intuition about typicality. The tension comes from the fact that all three are plausible, and the data are not yet rich enough to force a single verdict. Photometric redshift errors remain a leading systematic because broadband colors can be deceiving. A dusty lower Z galaxy can masquerade as a high Z dropout. An emission line boosted filter can shift the best fit redshift upward without any true high Z break. The probability distribution may still include the mundane solution, but the headline tends to follow the peak.
The discipline is to remember that a peak is not certainty.
A careful viewer should ask what the second best solution is and how much probability it still carries. Spectroscopic systematics can also intrude. A marginal line detection can be overweighted when it matches an exciting hypothesis. If the line is misidentified, the redshift collapses to a more ordinary value, and the age problem dissolves. The same spectrum can support two narratives until additional lines break the tie.
This is why follow-up is not a luxury. It is the method completing itself.
In practice, the difference between hint and measurement is often just more photons, gathered patiently over more observing time. Lensing, magnification, misestimates are another lever. Overestimate magnification, and you underestimate intrinsic luminosity and mass, changing how extreme the galaxy seems. Underestimate magnification, and you inflate the implied star formation and enrichment requirements.
The lens model is built from visible galaxies and assumptions about dark matter distribution, then tested against arcs and multiple images. Small model differences can matter when the claim is extraordinary. Even the inferred size of the galaxy can shift, and size feeds directly into surface brightness and star formation intensity. Selection bias is quieter but powerful. Surveys preferentially find the brightest and most compact objects, which may be brief starburst phases. The deep field is not a census of everything, because faint ordinary galaxies fall below detection. If we only see galaxies during their most luminous episodes, we may infer a maturity that is not typical. The universe may be full of quieter systems that we simply cannot yet hear. The question is whether Webb is revealing the common story or merely the loudest moments of a much larger population. Yet the oxygen implication remains sharp if both measurements survive. Oxygen means prior stellar death, which means prior star formation, which means a compressed and efficient early history. The logic is simple, and that simplicity is what makes it unsettling. If that history is common, then the early universe was more productive than many lambda CDM-based simulations predicted. It would mean that stars, metals, and ionizing photons arrived earlier in bulk. It would also shift how we think about reionization, because metals and ionizing light tend to travel together. That does not force a new cosmology immediately, but it does force new astrophysics. It may require different initial mass functions, different feedback coupling efficiencies, or different gas accretion behavior in the first halos. It may also require better treatment of radiation transport and metal mixing. These are not cosmetic adjustments, because they change how quickly galaxies can turn gas into light. The deeper implication is methodological. The early universe becomes a laboratory where our approximations are stress-tested under conditions we cannot reproduce. The tension is therefore a test of our assumptions about the first stars. It is also a test of our measurement chain, from imaging to extraction to line identification. Each link can fail quietly, and each link can be strengthened with targeted follow-up. The most productive posture is neither belief nor dismissal, but reconstruction, rebuilding the claim from the bottom up. In a sense, the chapter is not about a galaxy, but about how science behaves when it approaches the edge of what can be measured. The practical next step is more spectroscopy at higher signal-to-noise and broader wavelength coverage. Multiple lines reduce degeneracy and expose misidentifications. A secure redshift plus a consistent set of nebular diagnostics would turn the oxygen claim from provocative to unavoidable. With more coverage, the spectrum becomes less like a hint and more like a fingerprint. The goal is redundancy, because redundancy is what turns a fragile inference into a stable conclusion. Until then, the story stays balanced on conditional language. If z equals 14.32 is correct, the cosmic clock leaves only 290 million years. If oxygen is truly present, the galaxy carries evidence of earlier generations that should be scarce at that time. The conditional is not weakness. It is the honest shape of frontier science. It is also a reminder that nature does not care about our expectations, only about what the data can support. Maintain the tension, because the stakes are not one object, but a pattern. One anomaly can be a mistake or a rare peak. Several anomalies begin to reshape what we think is normal in the first few 100 million years. The question becomes unsettlingly practical. Are we seeing exceptions, or are we finally seeing the rule? If the rule is early efficiency,
then the first chapters of galaxy formation may need to be rewritten with less hesitation. And Z14.32 is not alone. A second case, described by some as a cosmic miracle, pushes unease from curiosity to trend.
The next chapter follows that second signal and asks whether the frontier is moving or whether our ruler is slipping. And Z1432 is not alone. A second early candidate arrives with its own headline language, and its discoverers call it a cosmic miracle. The phrase is not marketing. It is shorthand for tension, an uneasy mismatch between what the telescope records and what our timelines allow. The galaxy appears too bright for its supposed distance, too massive for its supposed age, and too organized for the era. It is the kind of object that makes a plot look wrong before anyone knows which assumption is guilty. In the Webb era, brightness is the first alarm bell, because photons are the currency of inference, and the early universe is expected to be stingy. At redshift above 10, flux should be scarce, and the luminosity function should fall steeply as the supply of massive halos thins. That expectation is not aesthetic, it is statistical. LCDM predicts fewer rare heavy halos as you climb to earlier times. Yet this object sits high on the curve, like a lighthouse where we expected only embers. Its inferred ultraviolet luminosity implies a star formation rate that seems disproportionate to the available time, especially when the cosmic clock grants only a few 100 million years. Even if gas is plentiful, turning it into stars fast enough requires unusually efficient cooling, unusually dense inflows, or both. When teams translate that light into stellar mass, the numbers swell, and the swelling itself becomes part of the story. The best-fit spectral models can imply billions of solar masses assembled within a few 100 million years, which is a demanding schedule for any theory of hierarchical growth. It is demanding because halos must form, merge, retain gas, and keep forming stars despite feedback that should blow gas back out. That is why the word miracle appears in papers and talks. It signals that standard expectations feel stretched before anyone claims new physics, before anyone rewrites a textbook, and before the community agrees on a single redshift. In astronomy, miracles often mean we are missing a correction, but sometimes they mean we are missing a mechanism. To appreciate the tension, it helps to picture what bright means at these distances. Webb collects infrared photons that began as ultraviolet starlight, then were stretched by expansion until their wavelengths doubled, tripled, and more. The telescope is not seeing a nearby beacon. It is catching a faint, reddened echo that should be vanishingly small. Each detected photon is a survivor of absorption by intergalactic hydrogen, detector noise, and the simple dimming of distance. Even the act of finding such a source is a triumph of technique. The detector stares for hours, stacking exposures while cosmic rays are rejected and background patterns are modeled away. Calibration frames remove subtle detector drifts, and careful mosaicing aligns stars to fractions of a pixel. In the final mosaic, the candidate appears as a compact smudge, just a few pixels across, yet it carries an argument about the early universe. The visuals almost hide the drama. A dark field is peppered with faint galaxies, and the miracle is a slightly brighter dot with a suspiciously sharp color break. That break is not just a color, it is a physical boundary. Ultraviolet light shortward of Lyman alpha is shredded by neutral hydrogen along the line of sight. Now, widen the frame beyond one object. Webb deep fields and lensing cluster programs keep producing similar candidates,
and the surprise becomes statistical rather than anecdotal. The story shifts from, "What is this galaxy?" to, "Why does the sky contain so many like it?" The shock is not only that one galaxy looks mature. The shock is that multiple bright candidates appear at Z greater than 10, then at Z greater than 12, and they do so across independent teams and independent reductions, different pipelines, different photometric apertures, different background models, and still the same uneasy brightness keeps resurfacing. In Lambda CDM, the earliest massive halos are rare peaks in the primordial density field. Those peaks originate in tiny fluctuations measured in the cosmic microwave background, then amplified by gravity over time. The predicted number density drops rapidly with redshift, so survey volume matters, and so does the probability of catching a rare fluctuation. A small field probes a narrow cosmic volume at extreme redshift, like looking through a drinking straw at a vast landscape. If it still contains several bright sources, the implied abundance rises uncomfortably fast, and the rare peak explanation begins to feel overworked. The straw is narrow not because Webb is small, but because the early universe offers only a thin slice of co-moving volume per unit redshift. This is where luminosity functions become a plot with stakes. Observers count galaxies per unit volume per unit brightness, then compare those counts to model curves that encode assumptions about halo growth, star formation efficiency, and feedback. The curves are not mere fits. They are compressed theories. Each bend reflects a balance between gravity pulling in and energy pushing out. Early Webb counts often sit above pre-Webb forecasts, especially at the bright end where theory predicted a sharp drop. That gap can shrink with revised completeness estimates and better treatment of contamination, but it has not vanished across all programs. The bright end matters because it is where rare halos live, and where small number statistics can still carry enormous leverage. The temptation is to treat the gap as a crisis, because a clean plot invites a clean verdict. The discipline is to ask how the gap could be manufactured by selection and by inference, since every step from pixel to physical mass contains a choice. In the history of deep surveys, apparent excesses have sometimes dissolved after better photometry and sometimes hardened into new populations. Start with the simplest bias. We do not see typical early galaxies. We see the brightest tail that survives detection thresholds, and that tail is not a fair sample of the underlying population. The earliest catalogs are, by design, lists of winners in a contest of visibility. At the edge of sensitivity, surveys are biased toward compact sources, because surface brightness matters as much as total light. Compact sources have higher surface brightness, and they are easier to detect against the infrared background and easier to separate from neighboring objects. A diffuse galaxy with the same total flux can be missed because its light is spread thinly across too many pixels. The same bias favors short-lived phases. A galaxy caught during a burst can dominate a catalog, even if the burst lasts briefly, because the selection is made on light rather than on time-averaged star formation. In other words, we may be catching fireworks and mistaking them for steady lamps. There is also a subtler bias in how candidates are defined. Dropout selection relies on a sharp color break between filters, which is interpreted as the Lyman break from hydrogen absorption. But other spectral features and noise fluctuations can mimic that break, especially when the object is faint. A dusty galaxy at lower redshift can also produce a steep apparent break, because dust reddening and older stars reshape the spectrum. Lensing adds another layer of distortion. Foreground mass can magnify background light, and a modest magnification can promote an ordinary source into a miracle. the way a curved glass can turn a candle into a flare.
The magnification also stretches apparent sizes, which can change detectability in ways that are hard to intuit. In cluster fields, the visual is dramatic. Webb images show arcs and stretched smears around giant ellipticals, and those arcs are the signatures of space-time curvature. The cluster's gravity acts like an optical element, splitting and warping background galaxies into multiple images. Behind them, faint galaxies are boosted, and the catalog becomes a blend of intrinsic brilliance and gravitational amplification. But lensing is model-dependent. If the magnification is wrong, then intrinsic luminosity and inferred mass are wrong in the same direction, because the correction multiplies everything we derive from the observed flux. Even a small error in magnification can move a point dramatically along the luminosity function's bright tail. Even without lensing, the translation from flux to mass is fragile. It rests on stellar population synthesis, and those models are assumption engines that compress complex astrophysics into a manageable set of templates. They are powerful because they connect colors to ages and masses, yet they are also brittle because early galaxies may not resemble the nearby calibrators. They assume an initial mass function, often similar to later galaxies, because that is what we can calibrate nearby. They assume a star formation history, often smooth or exponentially declining, because smooth histories are mathematically convenient and historically successful at lower redshift. They assume that stars form with familiar ratios of massive to low-mass objects, even though the first environments may favor different fragmentation. They assume dust attenuation curves that may not apply at very low metallicity, where grain composition and size distributions could differ. They assume that the observed light traces the bulk stellar population, even though a small fraction of very young stars can dominate the ultraviolet output. They also assume that starlight is the main power source, even when accretion could contribute. At z above 10, each assumption becomes a lever. Move one lever slightly, and the inferred mass can shift by factors, not percentages, because the mass-to-light ratio is the hinge on which the whole estimate swings. The same photometric points can be fit by a young low-mass burst or an older higher-mass population, and the difference is physically enormous. Nebular emission is a major lever, and it is easy to underestimate when working from broadband photometry. Strong emission lines can contaminate broadband filters, inflating the apparent continuum and pushing masses upward, even when the underlying stellar continuum is modest. This is especially treacherous because Webb's wide filters are designed to gather photons efficiently, not to isolate individual lines. The physics is straightforward, but unforgiving. Hot, massive stars flood their surroundings with ionizing photons, and the gas responds by glowing in discrete lines as electrons recombine and collide. Those lines can be so strong that, when redshifted into a wide filter, they masquerade as extra starlight. A single-line complex can lift a broadband flux by tens of %, which then propagates into a much larger mass estimate. The same lines can also fake a Balmer break. A line-boosted color can mimic an older stellar population, even when the stars are extremely young, and that false break nudges the fit toward higher ages and higher masses. The irony is that the brightest, most exciting galaxies may be the ones where this effect is most severe. Dust is another lever with two faces. Too much dust can hide star formation and bias ages older, while too little dust can bias masses higher, because the model compensates for blue light by adding more stars rather than by adding attenuation. In practice, dust and age can trade places in a fit, and the uncertainty is amplified when only a few filters bracket the break. In the early universe, dust itself is a moving target. Dust can form in supernova ejecta, but it can also be destroyed by shocks,
and the balance between formation and destruction may differ radically from later galaxies. Grain growth in dense clouds may be limited by time, while destruction can be immediate, and that asymmetry changes how quickly a galaxy can redden. Star formation histories are the quietest lever because they are rarely visible in a single snapshot. A bursty history can produce high luminosity per unit mass, making a young galaxy look massive, while an extended history spreads the light over time and lowers the instantaneous brilliance. In a burst, the ultraviolet output is dominated by stars that will die before the next major merger completes. Metallicity assumptions feed back into every fit. Low metallicity stars are bluer and more luminous, and that changes mass-to-light ratios in a direction that can either relieve or intensify the miracle, depending on the template grid. Low metallicity also changes stellar winds and ionizing output, which then changes nebular line strengths. The same parameter reshapes both continuum and lines. So the cosmic miracle can be partly a bookkeeping miracle. The galaxy is real, but the miracle may live in the conversion pipeline, in the way we translate a handful of colors into a population history. The deeper point is methodological. At the frontier, uncertainty is not an error bar. It is a branching tree of plausible interpretations. Still, the pattern remains even after caution. Some objects stay bright under multiple reductions, and some remain extreme under multiple template families, even when teams intentionally broaden priors and include nebular emission. When a result survives adversarial modeling, it earns the right to be taken seriously. That pushes the story back to physics. If the masses and rates are even roughly right, then early galaxy assembly was unusually efficient, and the universe wasted little time turning gas into stars. Efficiency here means not only forming stars, but keeping them, retaining baryons in shallow potential wells despite violent feedback. Efficiency can rise without breaking cosmology. Gas accretion can be rapid in dense early filaments, and cooling can be helped by high densities because the cooling rate increases when particles collide more often. In a denser universe, the same physical processes run faster, and the cadence of collapse can quicken. Rare peaks can collapse early. A galaxy in a high sigma region can begin forming stars sooner than a typical region, and it can keep being fed because the surrounding environment is overdense and the inflow is persistent. The cosmic web at these epochs is not a gentle network, it is a set of narrow rivers funneling gas into the first nodes. Extreme starbursts can compress the timeline. A compact gas reservoir can convert into stars quickly, then generate intense nebular emission, and the resulting ultraviolet output can make a small system look like a giant. The burst can also be self-limiting because the same massive stars that light the galaxy can disrupt the gas on short timescales. A top-heavy initial mass function can also help, at least in the sense of light production. More massive stars per unit mass means more ultraviolet light and faster oxygen production because the most massive stars burn quickly and end as core collapse supernovae. But that same top-heavy population changes the inferred mass because our usual conversions assume many faint, long-lived, low-mass stars. Black holes can complicate the readout further. Early accretion can harden the radiation field, boosting lines that we interpret as star formation, and the spectrum can become a composite of stellar and non-stellar power. In a compact early galaxy, an accreting black hole can be both small and influential, like a pilot flame inside a bright furnace. An active nucleus can also mimic maturity. Line ratios and continuum slopes can shift, and a small AGN can dominate a faint galaxy's spectrum, especially when the host is compact and the accretion is efficient. The danger is not that AGN exist, but that they can bias the very diagnostics used to infer stellar mass and age. Historically, astronomy has seen this confusion before. Quasars were once mysterious radio stars, and only later did the community accept that accretion could outshine an entire galaxy. In the Webb era, the question returns in miniature. How often does a black hole hide inside an early galaxy's glow? And if it does, how many miracles are actually accretion-powered imposters? Now return to oxygen, because oxygen is the anchor of the central question. Oxygen lines do not simply say bright, they say processed. Matter has been through stars and returned to gas. They are chemical timestamps, and they are also thermometers, because their strengths depend on temperature and ionization. The second galaxy's miracle status often includes chemical hints. Some candidates show strong O3 or other metal lines at implausibly early times, and those lines carry the implication that heavy elements already exist in the interstellar medium. In practice, the evidence can arrive indirectly first, as a broadband excess that suggests a line complex has entered a filter. To see why this matters, remember what oxygen is. Oxygen is not made in the Big Bang in meaningful amounts. It is forged in stellar interiors and dispersed by supernovae and winds. If oxygen is present, then at least one previous generation of massive stars has lived and died. Those stars must have formed, evolved, exploded, and mixed their yields into gas that is still dense enough to glow. But oxygen lines do not automatically mean near-solar metallicity. A trace enrichment can still produce detectable lines under high ionization conditions, because line strength depends on both abundance and excitation. A little oxygen can shout if the gas is hot, the radiation field is hard, and the density places the atoms in the right collisional regime. That distinction matters. Trace oxygen still requires prior stars, but it does not require a long, calm history of enrichment, and it does not require the slow buildup associated with many generations of low-mass stars. It points to rapid cycling, massive stars forming early, dying quickly, and enriching their surroundings on timescales of only a few million years. Strong O3 can be loud for reasons besides abundance. High electron temperatures and hard spectra can amplify collisionally excited lines, and low metallicity gas can actually run hotter because it cools less efficiently through metal lines. In other words, the line can be bright because the gas is extreme, not because the gas is rich. A young starburst with a hard ultraviolet spectrum can ionize oxygen to O++ efficiently, and the resulting emission can dominate a broadband measurement. That dominance can then feed back into mass estimates, because the same boosted flux is interpreted as extra continuum unless the line contribution is modeled correctly. So the correct inference is narrower. Oxygen implies at least one earlier generation of massive stars, then rapid dispersal into ionized gas, and then a geometry that lets us see the glowing regions without too much obscuration. It also implies that the galaxy's gas is not pristine, which matters for cooling and for the transition from the first stars to more familiar stellar populations. Even that narrow inference is unsettling at 290 million years. It forces the first stars to ignite early, die quickly, and enrich efficiently, while the galaxy is still assembling and while the surrounding intergalactic medium is only beginning to change. It also raises a quiet question. How early did the first star-forming pockets ignite, if we already see their chemical fingerprints here? The visual here is chemical, not just photometric. Imagine pockets of ionized gas around clusters of massive stars, their radiation carving bubbles in a neutral medium. In those bubbles, oxygen atoms are struck by electrons and flash in green-blue lines.
Then the expansion of the universe shifts that light into Webb's infrared detectors. Around the bubbles, darker lanes of neutral hydrogen wait, absorbing and reshaping the spectrum before it ever reaches us. To make the human scale legible, we need a timeline anchor. These galaxies are seen when Earth did not exist and the Sun was unformed, and even the Milky Way was still building its own structure. The Milky Way's oldest stars were only beginning to assemble into a recognizable halo, while these distant systems were already lighting up their neighborhoods. Complex life is far younger than this light. Sharks appeared only hundreds of millions of years ago, long after these photons began traveling, and long after the first oxygen in these galaxies was forged and scattered. The comparison is not a joke, it is a ruler, one that turns a redshift into a visceral sense of too soon. So the phrase, "younger than sharks," becomes a cognitive tool. It compresses cosmic time into a comparison that a viewer can feel because it ties a remote redshift to a familiar chapter of Earth's biological history. It also invites a thought. If complex ecosystems took billions of years to emerge here, what does it mean that heavy elements appeared so quickly out there? The galaxies are ancient to us, yet infant relative to the universe. The paradox is that they look chemically busy when we expect chemical silence, as if the cosmos began writing in ink before we thought it had invented a pen. And once you see one line of ink, you start scanning the page for more. Now ask why Webb finds too many of them. Part of the answer is that Webb opened new parameter space, and the first look is biased toward the spectacular because the observing strategies were designed to maximize discovery. Historically, the first deep surveys with Hubble also found surprises. Then later surveys mapped the mundane majority with larger samples. Early programs targeted lensing clusters and deep fields. Those strategies maximized the chance of finding extremes, not the chance of finding averages, because telescope time is precious and the first goal is to push boundaries. Deep fields trade area for depth, and lensing fields trade simplicity for magnification, and both trades favor the rare and bright. The survey volume at Z above 12 is small, but the selection is aggressive. It is designed to catch the brightest and most magnified sources, and it relies on color cuts that favor sharp breaks and high signal-to-noise detections. The result is a catalog that is excellent for discovering candidates, yet not automatically representative of the underlying population. That creates a statistical trap. If you search where extremes are amplified, you will conclude that extremes are common, and your intuition about the typical early galaxy will drift upward. The trap is subtle because the images feel like direct reality, even though they are a filtered reality shaped by exposure times and selection thresholds. Yet the trap does not fully dissolve the surprise. Even accounting for bias, some number counts remain high compared to conservative models, and the bright end tail still looks heavier than expected. When the same pattern persists across different fields, it becomes harder to blame a single cluster lens model or a single reduction choice. This is where the anomaly becomes a crowd. One outlier can be a rare peak, but several outliers suggest a shifted baseline, or at least a baseline that we have not measured correctly. The crowd does not prove a revolution, but it does force a careful inventory of what we assumed about the first few 100 million years. The baseline could shift through baryonic physics. Simulations may underpredict early star formation efficiency or overpredict feedback suppression, especially when feedback recipes are tuned to match later galaxies rather than the first ones. Early gas is denser, more pristine, and more rapidly accreted, and those differences can change how feedback couples to the surrounding medium. Feedback is not a single knob.
Supernovae inject energy and momentum, radiation pressure pushes on gas and dust, and photoionization heats the surrounding medium. In tiny early halos, these processes can either quench star formation or, paradoxically, compress gas into new bursts. The same explosion that clears a cavity can also drive a shell that collapses into the next generation. Radiation transport may be mismodeled. If ionizing photons are trapped differently, then cooling, pressure, and line emission change together, and the same galaxy can look dim or bright depending on how porous its gas is. Porosity is not a detail. It is a control parameter for how much ultraviolet light escapes and how much is reprocessed into nebular emission. Metal mixing may be mismodeled. If metals mix faster into dense gas, then oxygen lines can appear sooner and more widely, and the chemical signature of maturity can emerge in a system that is still dynamically young. If mixing is clumpy instead, a small enriched region can dominate the emission, while most of the gas remains nearly pristine. The baseline could also shift through measurement pipelines. Photometry, deblending, background subtraction, and template priors can bias redshifts, especially when the object is close to the detection limit and the field is crowded. A faint neighbor can leak flux into an aperture, and that leakage can reshape colors enough to move a photometric redshift peak. At Z above 10, a small redshift error is a large age error. Move the brake slightly, and the galaxy gains tens of millions of years, which is a long time when massive stars live only a few million years. That extra time is not cosmetic, it is chemically meaningful. That extra time is not cosmetic. At these epochs, tens of millions of years can add a full generation of massive stars and supernovae, and it can turn impossible enrichment into barely plausible enrichment. It can also change the inferred halo mass, because the abundance of massive halos evolves steeply with time in this regime. There is also the question of interlopers, a mundane possibility with dramatic consequences. A dusty, lower redshift galaxy can sometimes mimic the colors of a high redshift dropout, and a single misclassified object can distort the bright end of a small sample. The risk is highest when the candidate is bright enough to matter, yet faint enough that its colors carry large uncertainties. Spectroscopy is the arbiter, but spectroscopy is hard here. The lines are faint, the sky background is complex, and the redshifted features can land between atmospheric windows for ground-based telescopes. Webb helps, yet even Webb must integrate deeply to turn a candidate into a confirmed measurement. A confirmed line locks down redshift, and it also reveals whether broadband flux was inflated by emission features. So the fork in the road sharpens. Either early galaxies form faster than our recipes allow, or our inferences are inflated by modeling choices, or some combination of both is producing the illusion of a miracle. The honest answer may be mixed, because selection effects and real astrophysical extremes can coexist in the same catalog. A third branch sits deeper. If the cosmic clock is slightly off, then the ages we assign to these redshifts are systematically wrong, and the tension we feel may be partly a calendar problem. In that case, the galaxies are not less impressive, but the accusation of too early becomes less secure. Changing the clock is not easy. The clock is tied to lambda CDM parameters constrained by the CMB, and those constraints interlock tightly because the acoustic peaks encode geometry, matter density, and expansion history. The early universe left a precise imprint, and any late time adjustment must still fit that imprint without breaking the rest of the pattern. But the clock is already under stress elsewhere. The Hubble tension is a disagreement about expansion rate, and it is a disagreement about time, because a faster expansion today implies a different integrated history of the scale factor. The dispute is not merely about a number. It is about whether two methods of measuring the universe's stretch can be reconciled. Now connect the threads. If h0 is higher than the CMB inferred value, then the universe expands differently, and the Z to age mapping shifts, altering how much time early galaxies had to assemble. That shift could ease some early galaxy timing pressure, or it could worsen it depending on the model, because changing expansion history can also change structure growth. Either way, it changes the stakes, and it forces consistency checks across independent datasets. A model that gives early galaxies more time must still produce the right clustering, the right lensing statistics, and the right CMB peak structure. The miracle, in other words, cannot be solved in isolation. Webb was built to see first light, not to adjudicate H0. Yet Webb's data feed the same distance ladder, and they can move its rungs, because improved infrared resolution refines Cepheid measurements and reduces crowding errors in host galaxies. When you resolve stars more cleanly, you reduce blending, and blending is one of the quiet ways distances can drift. So the cosmic miracle galaxy is not only a galaxy story, it is a stress test of how we translate light into mass and redshift into time, and how we carry uncertainties through a chain of assumptions. The deeper theme is epistemic. At the edge of observation, the universe and the pipeline are both part of the experiment. The chapter's pattern is now clear. Webb's edge is not quiet and primitive. It looks crowded and chemically active, and it looks that way in multiple fields and through multiple analysis pipelines. The images feel like first contact, and the data feel like a challenge written in faint infrared ink. Unless we are being fooled, we could be fooled by selection, by lensing, by emission line contamination, or by priors baked into templates, small choices that become large conclusions at the frontier. The frontier is where systematic errors stop being footnotes and start being protagonists. Or we could be watching the universe reveal a faster early growth mode that would keep cosmology intact while rewriting baryonic history, and it would force simulations to treat early gas physics with greater realism. It would also reshape our expectations for reionization, because brighter early galaxies can ionize their surroundings more quickly. Or we could be facing a deeper revision. Dark matter properties, early expansion history, or new energy components could alter structure growth, changing how quickly rare peaks collapse and how early star formation ignites. Each possibility has a signature, and the job now is to separate signatures from mirages. At this stage, the honest posture is conditional. The crowd of anomalies does not yet convict lambda CDM, but it does demand a careful audit, and it demands patience with uncertainty as the sample grows. In astronomy, revolutions are often slow, because confirmation requires not just more objects, but better measurements of the same objects. Now the story turns from galaxies to the clock that dates them. If the distance ladder and the cosmic clock are even slightly off, inferred ages shift, and the meaning of too early changes with them. That leads directly into the Hubble tension. Webb did not merely observe it, it unexpectedly worsened it, and the next chapter follows that fracture. Now the story turns from galaxies to the clock that dates them. The oxygen claim at Z around 14.3 is only shocking if the calendar is right. That calendar is built from a single number that sounds simple, yet governs everything we infer from faint light. H0, the Hubble constant, is the expansion rate of the universe today, expressed as how fast space stretches per unit distance. On screen, it is easy to picture as a grid drawn across the cosmos, every square slowly swelling. In the nearby universe, h0 links redshift to distance, where recession velocities scale roughly linearly with distance. That relation is the modern echo of Edwin Hubble's original 1920s discovery, when galaxies first revealed that the universe is not static. Yet the constant is not merely a local slope on a plot, because it anchors the full expansion history once matter density and dark energy are specified. Once you choose those parameters, redshift becomes a timestamp, not just a stretch of wavelength. The same spectrum can imply different ages if the expansion history changes, because the mapping from Z to cosmic time is an integral over how fast the universe expanded at every earlier epoch. In practice, h0 is a conversion factor that turns observed brightness into distance, but it also sets the overall scale of the cosmic ruler. Distance then turns into luminosity, size, and inferred physical scale, which is why a single percentage shift echoes through many conclusions. Distance also sets the calibration of standard candles used to map the expanding universe. If h0 shifts, the latter shifts, and the inferred age of the universe shifts with it, along with the inferred time available for stars to live and die. This matters because the central question is a timing question, and timing is unforgiving at cosmic dawn. How can a galaxy, seen roughly 290 million years after the Big Bang, already show oxygen, a product of stellar furnaces and explosive deaths? Oxygen implies at least one earlier generation of massive stars, because primordial gas began almost entirely as hydrogen and helium. Those first heavy elements are forged through nuclear burning, then dispersed by winds and supernova shocks into surrounding gas. The number of available stellar lifetimes depends on how the cosmic clock maps Z to time, and at Z above 10, the margin can be only a handful of generations. Even a modest change in the clock can decide whether enrichment is merely fast or nearly impossible. Two measurement camps claim to measure the same h0 with high precision. They do not agree, and the disagreement has hardened over a decade as techniques matured and uncertainties tightened. The name for this is the Hubble tension, and it is not a vague discomfort. It is a numerical mismatch that refuses to shrink as data improve, which is exactly what precision science is supposed to prevent. The first camp measures the early universe and infers h0 indirectly. It starts with the cosmic microwave background, the afterglow of recombination at Z around 1100, when electrons and protons first combined into neutral atoms. Before that moment, photons scattered constantly off free electrons, and the universe was an opaque plasma. After recombination, light streamed freely, carrying a frozen pattern of tiny temperature variations across the sky. Planck measured the CMB power spectrum with extraordinary precision, turning those variations into a kind of cosmic fingerprint. Under the lambda CDM model, those peaks encode the sound horizon and the geometry of the universe. The sound horizon is the maximum distance pressure waves could travel in the early plasma before recombination, and it becomes a standard ruler imprinted in the CMB. The peak positions tell us the angular size of that ruler, which depends on the distance to the last scattering surface and the expansion history in between. The peak heights and damping tail add further information about baryon density, dark matter density, and the primordial fluctuation spectrum. From that early snapshot, LAM-CDM predicts a specific expansion rate today. The typical Planck value is about 67 to 68 kilometers per second per megaparsec, a number that feels abstract until you translate it. For every megaparsec of distance, galaxies recede about 67 to 68 kilometers per second faster because space itself is expanding. The uncertainty is small, roughly 1%, which is why the prediction carries such weight.
The inference is not just a fit, it is a tightly interlocked solution across multiple parameters. If you adjust one parameter, others must shift to preserve the observed peak pattern, like gears that cannot turn independently. That interlocking is a strength because it constrains the model strongly, but it is also a vulnerability. If the model is missing a component, the gears can still mesh while pointing to the wrong H0. The second camp measures the late universe directly, and it does so in a more tactile way. It builds a distance ladder, rung by rung, from the Milky Way outward, using objects whose intrinsic brightness can be inferred. First come geometric distances, like parallax, where Earth's orbit provides a baseline and nearby stars shift against the background. Modern parallax measurements, especially from Gaia, have made this rung far sturdier than it was a generation ago. Parallax calibrates Cepheid variable stars, luminous pulsators whose brightness rises and falls with a stable period. Cepheids have a period, luminosity relation, that turns pulsation timing into intrinsic brightness, which is why they are so valuable. The physics is rooted in stellar atmospheres, where partial ionization zones trap heat and drive rhythmic expansion and contraction. When you measure the period, you infer the luminosity, and when you compare luminosity to observed flux, you infer distance. Cepheids then calibrate Type 1a supernovae in the same host galaxies. Type 1a supernovae act as standardizable candles across cosmological distances because their light curves and colors correlate with peak brightness. The prevailing picture is a thermonuclear explosion of a white dwarf pushed toward instability, although the exact progenitor channels may vary. What matters for the latter is that, after correction, they can be compared across hundreds of megaparsecs. With supernovae, the latter reaches far enough to measure the slope of the Hubble diagram. That slope is H0, measured in the local universe, where the expansion dominates over most peculiar velocities. On a plot, it looks almost too clean. Redshift on one axis, brightness-derived distance on the other, and a line whose steepness encodes the cosmic expansion rate. Yet every rung beneath that line must be calibrated correctly, or the slope inherits the bias. The local distance ladder tends to find H0 around 72 to 74 kilometers per second per megaparsec. The uncertainty has also shrunk to about 1 to 2%, which is why the disagreement has become so consequential. The gap between 67 and 73 is only about 9%, a difference that might once have been shrugged off. Yet the error bars are so small that the discrepancy is statistically significant, and it persists across updates. That is what tension means in modern cosmology. It is not a dramatic factor of 2. It is a small percentage with high confidence, the kind that forces you to interrogate every assumption. It is a conflict between two precise answers that should converge if the model and the measurements are both sound. When precision rises and disagreement remains, suspicion turns to hidden systematics, quiet biases that move results without announcing themselves. Systematics are the first suspect because both methods are complicated, and complexity breeds subtle error. The CMB inference depends on a model, and the model could be incomplete in ways that mimic a different H0. The distance ladder depends on calibration, and calibration can drift through subtle biases in photometry, selection, and astrophysical environment. The scientific instinct is to search for the quiet error that could move a number by a few percent, because a few percent is all it takes. In the distance ladder, the quiet errors have names,
and they sound almost mundane. Dust extinction dims and reddens Cepheids, biasing inferred distances if not corrected, because the star appears fainter than it truly is. Crowding and blending in distant galaxies can make Cepheids look brighter than they are, because neighboring stars leak into the same resolution element. Metallicity can alter Cepheid luminosities and shift the period-luminosity relation, because stellar opacity and structure depend on heavy element content. In the supernova rung, selection effects can bias the sample toward brighter events, especially when surveys have flux limits. Host galaxy properties can correlate with standardized supernova brightness, hinting that environment leaves a residual imprint even after corrections. Photometric calibration across instruments can introduce small offsets that propagate into H0, because a tiny magnitude shift becomes a distance shift. Each effect is small, and that is the problem, because the tension is small and therefore easy to counterfeit. In the CMB inference, systematics are different in character, and they live in the microwave sky. Foregrounds from our own galaxy must be removed, and beam calibrations must be stable across frequencies and time. Planck's internal consistency is strong, and independent CMB experiments broadly agree on the key features. The larger vulnerability is conceptual, because the inference assumes lambda CDM is the correct bridge from Z around 1100 to today. So the tension becomes a fork, and each branch has consequences. Either the late universe measurements are biased high by systematics that have not been fully tamed, or the early universe inference is correct, and lambda CDM is missing something that changes the expansion history. The stakes are high because H0 is not an isolated parameter, and changing it ripples through the inferred age, the growth of structure, and the timing of reionization. Webb enters this story as an unexpected judge. Webb was built to see the first galaxies in infrared, not to settle a debate about H0. Yet the distance ladder is an infrared problem in disguise. Cepheids are easier to measure in the infrared, where dust effects are reduced, and the intrinsic scatter in their relation can be smaller. Infrared also improves contrast in crowded stellar fields, because cooler stars and dust emission behave differently across wavelengths. Visually, the difference is striking. In optical light, a spiral galaxy's disk looks like a glittering fog, with star-forming knots and dark lanes cutting across the view. In the near-infrared, the dust lanes fade, and individual stars separate more cleanly from the background glow. That change is not cosmetic, because it directly affects how accurately you can measure a Cepheid's brightness. Hubble Space Telescope did much of the classic Cepheid work, but it struggled in the most crowded regions. At tens of megaparsecs, a single Hubble pixel can contain multiple stars, especially in the dense inner parts of galaxies, where supernovae often occur. Blending makes Cepheids appear brighter, pushing distances smaller and H0 higher, because a brighter star seems closer than it is. Critics argued that crowding could be inflating the local H0, and that better resolution would soften the discrepancy. Webb's sharper infrared vision was expected to resolve that. Its point spread function in the near-infrared is stable and well characterized, which matters because precise photometry depends on knowing how light spreads across pixels. Its sensitivity allows cleaner measurements of Cepheids in supernova host galaxies, even when the background is bright. Its wavelength coverage reduces dependence on uncertain dust corrections because extinction is weaker and more predictable in the infrared. This was the hope, and it was a reasonable hope grounded in instrumentation. If the local H0 was biased high by blending and dust, Webb should pull it downward by making Cepheids look slightly fainter and therefore more distant. If the tension was a measurement artifact,
Better data should make the two camps converge, at least part way. Webb was supposed to be the instrument that turned tension into agreement, or at minimum, made one side yield. Instead, Webb sharpened the disagreement. Early Webb Cepheid observations remeasured key host galaxies with improved resolution, targeting the same systems that anchor the supernova calibration. The Cepheids did not dim enough to erase the high H0, and the inferred distances did not expand enough to reconcile with Planck. In some analyses, the recalibration confirmed the existing distance ladder scale, as if the ladder had been steadier than its critics hoped. The crucial detail is not only the central value, but the uncertainty, because uncertainty is where debates hide. Webb reduces scatter and Cepheid measurements by minimizing dust and crowding, which tightens the period-luminosity relation in practice. Reduced scatter tightens the calibration of supernova absolute magnitudes because fewer outliers distort the average. Tighter calibration shrinks the H0 error bars, and smaller error bars make disagreement harder to wave away. When error bars shrink and the central values stay separated, the tension grows in significance. The disagreement becomes harder to dismiss as noise, and it begins to look like a structural mismatch rather than a statistical accident. The story becomes more dramatic because the simplest escape route closes, and the audience can feel the trap tightening. Webb does not deliver a compromise number. It reinforces the split, and it does so with cleaner infrared data. This is the climax logic of the Hubble tension. Precision was supposed to heal the fracture, because better measurements usually converge on a common truth. Precision, instead, deepened it, like sharpening a blade that was already cutting. The universe is whispering two answers, and Webb made both whispers clearer, leaving us with a sharper contradiction rather than a resolution. Now connect this back to the oxygen problem. The galaxy at Z, around 14.3, is dated by integrating the expansion history back in time, which is why H0 matters, even when you are not measuring it directly. In lambda CDM, the age at a given redshift depends on H0 and the density parameters, because those parameters set how quickly the scale factor changes with time. Higher H0 generally implies a younger universe today, but the early time mapping depends on the full model, not just one number. At high redshift, the universe is matter and radiation dominated, so the details matter in a physically specific way. Radiation density falls faster with expansion than matter density, and that transition shapes the early clock rate. If you change H0 while keeping the CMB acoustic scale fixed, you often must change other parameters because the angular size of the sound horizon is tightly measured. Matter density, dark energy behavior, and the sound horizon can shift together, and the shifts can subtly change the inferred time available for early galaxy assembly. So the oxygen claim sits on a moving foundation. If the true H0 is closer to the local value, the integrated expansion history differs from Planck's lambda CDM solution, even if the difference seems small today. That can alter the age of the universe, and the age at Z around 14, which is the window in which the first stars must ignite and enrich their surroundings. It can also alter how quickly structures grow from primordial fluctuations, changing what kinds of halos exist to host early galaxies. Structure growth is the second bridge between H0 and early galaxies, and it is a bridge built from gravity. The abundance of massive halos at Z above 10 depends on the growth rate of density perturbations seeded in the early universe. Growth depends on matter density and the expansion rate, because expansion competes with gravitational collapse by stretching space faster than matter can fall inward. If the expansion history changes, the predicted number of early massive halos changes, and the rarity of bright galaxies changes with it. This is why the Hubble tension is not a parochial debate about a local number.
It touches the entire narrative of cosmic dawn, including how quickly the first galaxies can assemble and how efficiently they can turn gas into stars. It changes how rare the bright early galaxies should be and whether the oxygen-bearing systems are extreme outliers or expected pioneers. It also changes how much we must demand from star formation physics, which already operates near the edge of what simulations can robustly predict. If H0 is wrong on the local side, then the early galaxies remain a sharper problem. The timeline stays tight, and the models must explain rapid enrichment and rapid assembly with little room for delay. The oxygen line then pressures astrophysical recipes like initial mass functions and feedback coupling because massive stars must form quickly and recycle material efficiently. The clock stays strict, and the galaxies look too mature, as if they have lived longer than the universe allows. If H0 is not wrong on the local side, then the model bridge from the CMB to today is incomplete, and that incompleteness must be specific. The CMB inference would be pointing to missing physics in the early universe, not merely a bookkeeping error. That missing physics would have to raise the inferred H0 while preserving the CMB peak structure, which is a difficult constraint. It would also need to remain consistent with baryon acoustic oscillations and lensing, which act like additional locks on the same door. This is where new physics enters, and it enters with constraints rather than freedom. Any fix must change the expansion history before recombination or around it, because the CMB locks the sound horizon with high precision. If you reduce the sound horizon, you can fit a higher H0 while keeping the observed angular scale, because a smaller ruler can appear the same size if the distance changes appropriately. But changing the sound horizon requires additional energy density or altered dynamics in the early universe, and those changes leave fingerprints elsewhere. One proposed avenue is early dark energy. It adds a temporary energy component that becomes significant before recombination, then decays away so it does not dominate today. That speeds up expansion early, shrinking the sound horizon, and it can move the inferred H0 upward. The burden is to match the full CMB spectrum without spoiling structure growth and lensing, because early changes can suppress or enhance clustering in ways we can measure. Another avenue is extra-relativistic species, often parameterized as NEF. Additional light particles increase the radiation density in the early universe, which also speeds early expansion and shrinks the sound horizon. The burden is to remain consistent with primordial nucleosynthesis, because the early expansion rate affects the production of light elements like helium and deuterium. It must also fit the CMB damping tail, where small-scale anisotropies are sensitive to radiation content. Modified gravity is a broader class of ideas, and it is tempting because it can reshape both expansion and growth. It changes how gravity behaves across cosmic scales, altering the relation between matter and curvature, and sometimes mimicking dark energy behavior. Some models can shift inferred parameters while leaving certain distance measures nearly intact, at least superficially. The burden is to satisfy solar system tests, gravitational wave constraints, and large-scale structure observations simultaneously, which is a demanding combination. Interacting dark matter, or dark radiation, can also shift the inference, because interactions change how perturbations evolve. If dark matter couples to another component, the evolution of density fluctuations and the acoustic features in the CMB can change. That can alter the CMB peaks and the inferred parameters, sometimes allowing a higher H0. The burden is to avoid erasing small-scale structure in ways that conflict with galaxy clustering and lensing, because the universe keeps careful records of how matter clumps. Evolving dark energy is another possibility, where the equation of state differs from a pure cosmological constant.
That mostly affects late-time expansion, and it struggles to solve the tension alone because BAO and supernova distances already constrain the recent expansion history tightly. Late-time changes often conflict with supernova and BAO distance measurements, trading one mismatch for another. The burden is to improve the fit without creating new tensions elsewhere, because cosmology is now a network of cross-checks. Across all these ideas, the standard of proof is high. A successful model must fit Planck, BAO, supernovae, lensing, and local distance ladder data together, not merely one subset. It must also preserve the success of lambda CDM in explaining structure formation and the CMB, which is why the community moves cautiously. The Hubble tension is not an invitation to invent. It is a demand for coherence across many precise datasets. Now return to systematics, because the community is not eager to abandon lambda CDM without exhausting the mundane explanations. The distance ladder is being cross-checked with independent techniques that rely on different astrophysics. Tip of the red giant branch distances provide an alternative to Cepheids, using a relatively sharp luminosity feature in old stellar populations. Strong lensing time delays offer another route to H0, turning the geometry of spacetime into a clock through variable quasars. Megamasers provide geometric distances in a few galaxies, where water vapor clouds orbit supermassive black holes and trace precise Keplerian motions. These methods do not yet converge on a single answer, but they map the battlefield with multiple lines of evidence. Some favor intermediate values, some lean high, and some align closer to Planck, suggesting that calibration and selection still matter. Yet Webb's Cepheid work makes it harder to blame the entire tension on crowding alone, because the infrared view removes one of the most plausible culprits. The deeper implication is psychological as well as scientific, because cosmology has lived for decades with a sense of closure. Lambda CDM, with its dark matter and dark energy, fit almost everything with a small set of parameters, and that success shaped expectations. The Hubble tension reopens that closure, not by overthrowing the model outright, but by revealing a seam where the fit strains. It says that precision is exposing a join in the story, and joins are where hidden assumptions tend to live. And that seam runs directly under the oxygen mystery. If early galaxies look too chemically evolved, we ask whether astrophysics is faster than we thought, with star formation igniting earlier and recycling material more efficiently. If the expansion rate refuses to agree with itself, we ask whether the cosmic clock is misbuilt, even if every gear looks polished. The edge of the universe is whispering two contradictions at once, and neither is easily silenced. One contradiction is chemical. Oxygen appears where we expected near-pristine gas, forcing rapid star formation and rapid recycling through short-lived massive stars. The other contradiction is geometric. The universe's expansion rate depends on how you measure it, and the two best measurements disagree despite years of refinement. Together, they create a suspenseful choice that is not yet a choice, because the evidence does not let us commit. Either the early galaxies are teaching us new baryonic efficiency, while cosmology remains intact and the clock stays as Planck predicts, or cosmology is missing a component, and the early galaxies are the first beneficiaries of a revised timeline and altered growth history. Or both are partly true, and the real story is a careful redistribution of error and physics across multiple measurements. In this chapter, Webb plays an ironic role because it was expected to reduce ambiguity by improving infrared measurements. It did reduce ambiguity, but it did not reduce conflict. It tightened the ladder and left the disagreement standing, which is a different kind of clarity. clarity that sharpens questions rather than answers them. The result is a sharpened question about time, and time is the currency of cosmic dawn. How many millions of years separate the first stars from the oxygen line we claim to see? And how many cycles of birth and death can fit inside that interval? How many mergers and bursts can fit before Z around 14.3, when even a brief pause becomes significant? Whether the universe had more time than we think because the expansion history is different, or whether it used the time it had with startling efficiency. The Hubble tension also changes how we interpret the crowd of early bright galaxies, because abundance is a test of both cosmology and astrophysics. If structure growth must be faster, that pushes on dark matter behavior and initial conditions. And if growth is unchanged, then star formation efficiency must be higher in early halos. Either way, the early universe becomes a stress test of multiple assumptions at once: how gas cools, how feedback regulates star formation, and how quickly halos assemble. Now hold the mystery rather than resolve it. The most unsettling outcomes are still plausible, and the data are still incomplete, which is why the tension remains productive rather than merely frustrating. Webb has made the contradictions harder to ignore, but not yet possible to settle with a single decisive observation. Resolving this requires more than a few deep fields and a few host galaxies. It requires wider surveys to beat down cosmic variance, because a small patch of sky can be unrepresentative at the bright end. It requires better spectra to lock redshifts and line identifications beyond doubt, because one misidentified line can masquerade as a profound discovery. It requires a distance ladder that is redundant across methods, not dependent on one rung that could quietly flex. That next wave is already planned, and it is designed to trade depth for breadth without giving up infrared sensitivity. A telescope designed for wide-field infrared surveys will map supernovae, lensing, and large-scale structure at scale, building the statistical backbone that Webb's pinpoint discoveries demand. It will not replace Webb's depth, but it will multiply the sample size and provide the kind of uniform datasets that precision cosmology thrives on. Enter the Nancy Grace Roman Space Telescope. Roman will survey large areas with Hubble-class resolution in the infrared, producing images that look like vast mosaics rather than narrow windows. It will find thousands of supernovae and measure weak lensing across billions of galaxies, turning subtle shape distortions into maps of dark matter. It will test the expansion history and growth of structure with statistical power, tightening the web of constraints that any solution must satisfy. The oxygen line at the edge of the universe and the Hubble tension in our cosmic backyard are not separate mysteries. They are two ways the universe challenges our conversion from light to time, from observed photons to a narrative of cosmic history. Webb has shown us the frontier and tightened the ruler, and the ruler still does not agree with itself. The next chapter follows the data flood that might finally force the contradictions into a single story, or reveal that the seam runs deeper than we imagined. Now hold the mystery rather than resolve it. Webb's next step is repeat spectroscopy, higher signal-to-noise, cleaner calibration, and multiple line confirmation to kill confusion and low redshift interlopers. Deeper spectra must pin oxygen with consistent O3, H-beta, and continuum breaks, not one fragile feature. That means resolving line shapes, checking relative strengths, and watching how the spectrum behaves across separate instrument settings. Cross-checks follow. ALMA can test dust and C2, tracing cold gas that should accompany rapid enrichment,
while extremely large telescopes add independent line ratios and redshifts at sharper spectral resolution. Multi-wavelength constraints stabilize masses, metallicities, and star formation histories that templates can overfit, especially when a single bright line dominates the fit. Then widen the frame beyond one object. Roman's wide infrared surveys will find large high-Z samples, reducing cosmic variance and selection bias, and catching rare bright systems systematically. It echoes an older lesson from Hubble deep fields. Small areas can mislead when the universe is lumpy. Webb stays the deep scalpel. Roman becomes the statistical net. Outcomes split. The anomaly fades. Physics updates. Faster enrichment, a different IMF, or feedback that seeds metals earlier than expected. Or cosmology shifts beyond lambda CDM. Oxygen at 290 million years is not impossible, but it stress tests every link. At the edge, faraway light interrogates our model, and science listens. Out at the edge of Webb's reach, we followed a single faint spectrum as it turned into a chain of inferences, each link carrying its own uncertainty. We watched how an apparent oxygen line becomes a claim about prior stars, how redshift becomes a calendar date, and how lambda CDM quietly supplies the ruler that makes 290 million years sound definite. And we saw why one strange object matters more when it is joined by a crowd, a bright end excess that could be new astrophysics, a measurement mirage, or a stress test of the cosmic blueprint itself. Webb's power is not only its mirror, it is its ability to turn stretched infrared light into a forensic record. But forensics demand corroboration. At Z around 14, a tiny shift in wavelength can move a galaxy across tens of millions of years, and a single feature can be tempted into the wrong identity when noise, absorption, and calibration all push back. That is why the real story became the reconstruction. Photons to spectrum to redshift to age to chemistry, and the uncomfortable realization that the most vulnerable link may change from object to object. Sometimes it is the line identification, sometimes it is the photometric dropout that promoted a candidate too quickly, and sometimes it is the model assumptions that translate flux into mass, maturity, and metallicity. Even if the oxygen signal holds, it does not automatically mean a calm, settled galaxy quietly aging in the early dark. Strong 3 can be the signature of extreme ionization, fierce temperatures, and a top-heavy initial mass function, a few violent regions dominating the light and making youth look like experience. But if oxygen truly is present, then some stars had to live fast and die early, and the first galaxies had to trap, mix, and recycle their metals with startling efficiency. That possibility does not break physics, it sharpens it, forcing our recipes for star formation, feedback, and early accretion to compete against what the universe actually wrote into the spectrum. And if the signal does not hold, that outcome is not a defeat either, because it tells us where the frontier really is. It tells us how easily selection can favor compact, bursty sources, how lensing models can quietly inflate brightness, and how template fitting can turn one bright line into a whole history. It reminds us that Webb is a deep scalpel, not a wide net, and that the first chapters of cosmic history cannot be reconstructed from a single dramatic frame. That is why the next steps matter. Higher signal-to-noise spectra with multiple line confirmation, independent reductions that agree on the same redshift, and cross-checks from ALMA, extremely large telescopes, and eventually Roman's statistical sweep. In the background, the clock kept ticking. because the oxygen problem is only shocking if the calendar is right.
LUM-CDM has earned its status by unifying the CMB, structure growth, and expansion into one coherent story. Yet, coherence is not immunity to revision. Small parameter shifts can soften or sharpen the too early tension, and the broader Hubble disagreement reminds us that our most famous number, the expansion rate, still has unfinished business.
Whether the solution lives in better data, better galaxy physics, or a new ingredient in cosmology, the point is the same. The universe is not obligated to be simple just because our model is elegant. So what are we really seeing? An impossible galaxy? A mistaken distance? Or a crack in the timeline that sets the age and expansion of the universe? The most honest answer, for now, is that we are seeing a test, where every link in the inference chain must be challenged until only the resilient story remains. If oxygen is confirmed at that epoch, then the first stars enrich the cosmos with breathtaking speed. And if it is not, then the frontier has revealed exactly how easy it is to misread a whisper at the limits of detection. Either way, the troubling question does not vanish. It matures into a better one. Which part of our translation from light to history is still incomplete? At the edge of the observable universe, distance is not just space, it is time, and time is written in chemistry we can barely see. Webb has not handed us a contradiction, it has handed us a clue. And the clue is that cosmology is not a monument, it is a living map, redrawn whenever new light arrives. Watch for the confirming lines, the independent reductions, and the wider Roman samples, because the next decisive discovery may be not a new object, but a new consensus.